Good evening to all the participants. So,
Good evening.
yes, sir. And as the time is up, shall we start now? Okay. So, yes,
Go.
thank you for the confirmation. Good evening to all the respected dignitaries, esteemed faculty members, research scholars from various research centers, PG students, and to all the participants. It's my honor and pleasure to welcome you all to this 6 days ATAL Faculty Development Program. This program is a valuable platform for enhancing knowledge, skills, and research capabilities in cutting-edge areas of technology and education. As we embark on this journey of learning and collaboration, let us embrace the spirit of innovation and excellence that ATAL Academy fosters across the nation. Over the next few days, we will be enriched by expert sessions, engaging discussions, and opportunities to share insights that will empower us as educators and researchers. Thank you all for your enthusiastic participation, and we look forward to a productive and inspiring FDP. On this occasion, I welcome Program Coordinator and also our Honorable Principal Dr. V.A. Kulkarni sir for this. And I now request Dr. M.S. Sannaikar sir to deliver a welcome speech.
Thank you, sir. Thank you so much. Good evening, everyone. It gives me immense pleasure to extend a warm welcome to all participants, distinguished speakers, and guests gathered here for this one-week faculty development program on quantum-driven semiconductors, fabrication, function, and future, organized by the Department of Physics, KLSVDIT, Haliyal. Semiconductors have truly revolutionized modern science and technology, from smartphones, computers, and LEDs to medical imaging, satellites, and renewable energy systems. Semiconductors are the invisible engines that power our connected world. Their capacity to control the flow of electrons with precision has made them the backbone of technological progress. Today, as we step into the quantum era, semiconductor research is reaching deeper dimensions, merging with the quantum mechanics to create devices of unparalleled efficiency, speed, and performance. This FDP has been thoughtfully designed to illuminate these exciting frontiers. Over the coming week, we will explore a spectrum of topics ranging from semiconductor nanostructures, quantum materials, fabrication techniques, device applications, and emerging trends in nanoscale engineering. These sessions will not only enhance our theoretical understanding, but will also inspire innovative pedagogical and research approaches. We truly honored to have eminent speakers from prestigious foreign universities, IITs, and leading industries. Their presence brings immense value, offering us the privilege to learn from their vast research experience and global perspective. On behalf of the organizing committee, I would like to express our heartfelt gratitude to our KLS management for their unwavering support and encouragement in organizing this event. We are deeply thankful to our beloved principal sir, whose continuous motivation and guidance have been instrumental in making this FDP a reality. So thank you, sir, and welcome you, sir, for this function. A warm appreciation also goes to all my colleagues and faculty members whose cooperation, enthusiasm, and teamwork have added a great energy and spirit to this program. To all our esteemed participants, on behalf of organizing committee, I wish you a week filled with insightful discussions and renewed inspiration in teaching and research journey. May this FDP ignite a shared passion for exploring the quantum-driven future of semiconductors. Once again, A very warm welcome to everyone. Thank you, and let's begin this wonderful journey of learning and discovery together. Thank you, one and all, and welcome to all. Thank you, sir.
Thank you, Sannaikar sir. It was really a warm welcome. And now I request our beloved principal, Dr. V.A. Kulkarni sir, to formally inaugurate this FDP.
Sure, Dr. Kalini.
Thank you, sir. Thank you very much. And now, after this digital inauguration and lighting of lamp, I request our Honorable Principal, Dr. V.A. Kulkarni sir, to give his inaugural address. Sir.
Yes, sir. Thank you. Good evening, all. I welcome all the participants for this AICT ATAL sponsored faculty development program on quantum-driven semiconductors, fabrication, function, and future, being conducted at KLSVDIT Deshpande Institute of Technology, Haliyal. This FDP brings together eminent experts and active researchers in the emerging domain of quantum semiconductor technologies. I am very happy that the resource persons from different spectrum, including two international experts from reputed foreign universities, distinguished speakers from IITs, eminent speaker from semiconductor industry, and from various reputed institutions and research organizations across India, are enlightening the participants on various aspects of quantum-driven semiconductors. And I am also happy that more than 100 participants are taking active part in the FDP. A majority of the participants are from electronics and communication engineering, computer science, and VLSI design domains. Several research scholars working in the areas such as material science, VLSI, optoelectronics, and semiconductor nanostructure are also participating. This FDP aims to provide a comprehensive understanding of the fabrication techniques, device functionality, and futuristic applications of quantum-driven semiconductor technologies. It serves as a platform for meaningful academic and research interactions among faculty, industry experts, and scholars. This initiative aligns with our institute's vision of transforming through technology by fostering advanced learning and research culture in the frontier areas of science and engineering. Once again, I welcome all the participants and speakers on behalf of Karnataka Law Society Management, on behalf of all the staff of Karnataka Law Society Vishwanath Deshpande Institute of Technology, Haliyal. My best wishes and congratulations to the coordinators, Dr. Samir Galgali and Dr. M.S. Sannaikar. Thank you.
Thank you, sir.
Thank you very much, sir, for this inaugural address. And on behalf of organizing committee, I thank you, sir. And now, dear participants, I would be very happy and pleasure in introducing you to the today's invited speaker. His name is Dr. Goni Basappa Pujar, and it would be my immense pleasure and honor to introduce you all to the eminent personality of Dr. G.S. Pujar. Dr. Pujar is currently working as Assistant Professor and Head Department of Physics and former Deputy Registrar Evaluation at GM University, Davangere. Dr. Pujar completed BSc in the year 2009 from Karnataka University, Dharwad, India, and subsequently acquired MSc in physics from Department of Studies in Physics from Karnataka University, Dharwad, in area of solid state physics. Qualified KSET in the year 2013 and awarded PhD in the year 2018 in the area of fluorescence spectroscopic study of some organic compounds and nanostructures under the able guidance of Professor Sanjeev Inamdar, Professor in the Department of Physics, Karnataka University, Dharwad. During his tenure in various institutions, Pujar worked in a variety of capacities like Project Fellow, PhD Research Scholar, Assistant Professor, Associate Professor, Head of Department of Research Center, etc. He has also taken the departmental responsibilities in the 2019 at GMIT and presently GM University, and currently leading the Department of Physics at GFGC Harpanahandi. During 14 plus years of teaching and research, which includes 5 years as research scholar, published 3 Indian patents and 1 book, and 30 plus research articles in various refereed international and national journals with a citation of 563 H index of 15, and presented 30 plus research articles in various conferences across India as well as in abroad like Italy. One research scholar has been awarded PhD degree from VTU Belgavi under his guidance, and currently 2 research scholars are pursuing PhD degree. Received international travel grant given to young scientists by DST, Government of India. Best paper awards for his 4 papers, that 2 oral presentations. Research fellowships. Received Best Project of the Year 2021 by Karnataka State Council for Science and Technology under 44th series, which is now selected for Faculty Project Program at KSCST. The Rockweight, a gaming app developed by Dr. Pujar and CSC students, have been selected for Power Judge Round of Grand Finale National Level Toykathon competition held in the year 2021, conducted by Government of India. Dr. Pujar is a life member of ISTE, and he is a member of ACS, ISCA, IERP, etc. And he is also a doctoral committee member for GM University, Davangere. With these brief words, I now present before you today's eminent speaker, Dr. G.H. Pujar. Sir,
Thank you, sir. Thank you so much, sir, for wonderful introduction. Thank you, sir.
sir, you can present your PPT
Yes,
now.
sir. Yes, sir. Yes, sir. Shall I confirm? Hope my screen is visible.
Yes, sir,
Yes,
your
sir.
screen is visible, sir.
Yes, sir. Once again, confirm me. So, is it visible, sir?
Sir, yes, sir, it is visible.
So, very good evening to all of you, and thank you for wonderful introduction by Kalgali, sir. Before my talk, I would like to thank all the organizers for providing this opportunity, and also thank you all for having me in this platform. This is ATAL Online 6 Days Faculty Development Program organized by KLS Vishwanath Rao Deshpande Institute of Technology, sponsored by AICT under ATAL program. So I would like to share with you all the topic entitled, that is Introduction to Nano Semiconductors. Presently, I'm working as assistant professor and head of the department at GFCC Harpanahandi. So this is what I would like to share with you all today. This is what outline of my talk, where I divide my whole talk into 3 parts. In first part, I would like to touch about this brief introduction about semiconductors and need for nano semiconductors, and also would like to cover some different types of nano semiconductors. In the later part, so I would like to focus about some core properties of nanosemiconductors and their measurement by discussing different techniques of synthesis and different methods of characterization and fabrication techniques. And lastly, I would like to touch about some important applications or innovations and also some future trends of these nanosemiconductors. So before start of this one, I would like to just connect with you people. So if you are all comfortable to access your cell phones, can you able to access your cell phones? Can you confirm anybody? I repeat, can anybody answer my question? Can you access your cell phones now?
Yes, sir. Yes,
Yes.
sir.
Sir,
Yes, sir.
yes, thank you. Thank you for the confirmation. Just go to Google. Just I would like to connect with you people. At what extent you know the title topic today? Just go to Google and type slido.com. Just follow my instruction. Just go to Google, type slido.com. Once you click, then it is asking for code. You just mention, type this code, that is 3135940. Then you will able to see this question. So can you read the question carefully and can you able to answer? Anybody? And also confirm if you are facing any technical issues.
Yes, sir. Question is visible, sir.
Yes, yes. So on a scale of 1 to 5, where 1 is completely new and 5 is you are expert in this topic. In that manner, you just read the question. How familiar are you with the concept of nanosemiconductor? If you are completely new, you can opt for 1. If you are already familiar, you can go for 5.
He was expert at 100.
I repeat, here the scale is 1 to 5. 1 means you are completely new. You've never heard this kind of concepts, nanosemiconductor. Little bit if you know, you can go for 2. In the medium range, you can opt for 3, like that. If you are completely expert in this field, you go for 5.
China.
So I have seen almost more than 50 plus participants are there, but only around I have received right now only 9-10 members response. Sorry. So here I have seen only one candidate is very new to this one. 4 candidates opt for 2 candidates for 3, and 5 members are expert in this nano semiconductor. Still, if you need time, I will not go to the next slide. Okay, thank you for your response. So be in that site only. I would like to ask one more question. So what comes to your mind when you hear the term nano semiconductors? Can you able to just type your answer? Whatever comes to your mind, just type it and enter. Semiconductors which are in the range 1 to 100. Absolutely correct. It's a concept of physics. Okay. So right now 2 participants have answered. Nanometer scale. Small scale semiconductors, nanomaterials. Absolutely. Are also quantum dots, correct? Quantum wires, quantum dots. Perfect. Even you can opt for multiple options also. If you have anything other than these words, you can go and type in the same site. You have option to enter multiple words. So well, thank you. So absolutely, it defines the nano semiconductors. Whatever you said, absolutely right. So then let us have some brief fundamentals or introduction about this nano semiconductors. So before nano semiconductors, I would like to throw some light on the how exactly semiconductors originates first. So just have some flashback into the world of materials, how the materials evaluation has been taken place, and finally how we have reached the semiconductor material. So the semiconducting material, it is the era it is the era which we are living now. So just have some flashback. So I will have some on 5 minutes VT how exactly the materials has been evolved here. So just look at this VT. Can I confirm both audio and display is visible?
Yes, sir.
Anybody?
Yes, sir.
Yes,
Sir.
thank you.
Yes, sir. Yes.
Sir, I would like to interrupt you, sir. Sorry for that.
Okay.
It's video is okay, sir, but so no audio is not. I think it's not working.
Audio is not working.
Yes, sir.
Okay. One. Screen is visible.
Is visible.
Now audio.
No.
No.
No, sir. No, sir. No, sir.
No audio. What I have to do? Is there any technical team? How can I get this audio?
Mm,
Can I get any technical help?
yes. I think mic is also on speaker.
Yeah. Just wait a minute. I'll check with the settings.
Things we
Now
use in our
is
daily
it
life,
audible?
which require usage of materials like concrete.
I'm sorry.
Everything
How's
around
about
us
now?
is made of something.
Yes, it's
Is it
now
audible?
fine, sir. Yes, sir, fine.
Everything
audible.
around,
It's audible, sir.
everything around us is everything around us is made of something.
Is it audible now?
Human is our clothes, our home, things we use in our day.
Is it audible?
Other things.
No, sir. First, initially it was. Now it's no. Little bit, yeah. I think you can increase the volume there.
The digital world is not just technology and culture. It is very much part of it because we invented it.
Yes.
One minute. ಅಲ್ಲಲ್ಲ ಫೋನ್ ಆಗಲ್ಲ ಸರ್. Now audible, sir?
Sir, it is audible, sir. Go ahead. Hello, sir. Sir, is it audio?
Yes, sir. I am. You are audible now.
Sir, you are also audible, sir. Go ahead, sir.
Go ahead. How's about the video's audio? No.
Video is there, sir, but audio is not appearing, I guess.
Okay. Leave it, sir. No issues.
PPT is visible, sir, now.
PPT is visible, right?
Yes, sir.
One minute.
Only video is rolling, sir, but audio is not there.
Is there any technical error? Can I get any technical help, sir? Microsoft Teams.
I will find out, sir. 1 second, please.
Patil.
Sir, PPT is visible now.
Sir, better. I will skip this video. No issues.
Yes, sir. Yes, sir. No problems. We will come back again, sir. No issues.
Yes, sir. No issues. No issues.
Yes, sir.
Thank you,
Yes,
sir.
sir. Sure, sure.
Thank
Okay.
you. So this is what I would like to highlight in that video. That is how the material evaluation takes place from Stone Age, then followed by Bronze, then Iron Age has come, then Modern Age. Now we are in the era of computer age, that is Silicon Age, where we are using most of the things in the world that is made by the semiconductors. This is what actually I would like to highlight in that video. That's all. So we know that the whole universe is made up of space and energy. How exactly the semiconductor has been evolved from the particles, this is what I would like to highlight here. Where energy is again made by particles and fields. We know that there are two types of particles. One is atomic and non-atomic particles. In the atomic, when I say atomic world, that is, we enter the era of material science, where the atoms, based on their band structure, we can broadly classify all the materials into mainly that is three categories. One is conductors, semiconductors, and insulators. I will not go all the details of this material science, where I would like to highlight this, but how exactly the materials the classification has takes place. So based on the band structure, we know that the broadly all the materials present in the universe broadly classified into three categories. One is insulators, semiconductors, conductors. So we know that in the insulator band gap is very large, and in the semiconductor the moderate band gap we have. In the conductors there is no band gap. So again, in the semiconductors we have two types. There is one is intrinsic, another one is extrinsic. Intrinsic is the pure form of semiconductor, and extrinsic is the that is by adding some dopants we have. Based on the doping, again we have in the extrinsic two types. One is P type and another one is N type. So this basics we already knew it most of the things. So where the classification is completely based on the band structure. So what exactly a semiconductor means, we are already familiar with the definition that, so based on the electrical conductivity, we can say, so the materials which show the electrical conductivity between the conductors and insulators. In terms of resistance, where conductors, we knew that the resistance is very, very low, that is of the order of 10 to minus 10, whereas insulators, the resistivity is very high, that is of the order of 10 to minus 18. So in between these, in order to fill the bridge between a bridge that is gap between these conductor and insulators, semiconductor materials have played a significant role, and we have all the control over their electrical and optical properties. So we know that without any semiconductors, nothing in this world that is built today exists. Approximately, we can say this statement where almost in all the fields of field and that is fields of science and technology, we have this word that is semiconductors. So we have nothing to do with that is without semiconductors, no communication, and even we entered that is EV vehicles where abundantly semiconductor metals are being used, even in terms of services that is ATM services, chip services, SIM services, and all that wherever we have. So everything approximately built by one or the other way that is semiconducting materials. So this is all about semiconductors. So next we come to that is our topic, that is title topic, that is nano semiconductors. So what exactly the nano semiconductor means? So most of the participants have already answered in the first slide itself what are exactly the nano semiconductors means. So as that name itself indicates that nano semiconductors are semiconducting materials, or they have the behavior of semiconductors, and they are precisely engineered at the nanoscale, typically in the range from 1 to 100 nanometer. So any material dimension which lies in this range we can call, and also that material has to exhibit the property of semiconducting behavior as I explained in the previous slide. So whose electrical properties should be lies between the conductors and insulators. Such semiconducting materials in the range 1 to 100 nanometer are called as nanosemiconductor. So we knew that at this nanoscale, the materials exhibit the tremendous and unique quantum properties. So due to the one of the important phenomena in the quantum mechanics called quantum confinement effects. And this details very in the next session that is will be delivered by Dr. Ravi Raj Kashikar from IIT. He will be giving all the details about this quantum confinement and how the band gap engineering will be made. So that kind of details will be delivered very soon in the next session. So this nano semiconductors bridge the gap between, as I said, metals and insulating properties. So they offer the tunable electrical and optical properties, that is behaviors that enable revolutionary applications in various fields of science and technology. So their size dependent properties allow all the scientists and engineers to customize the desirable performance for various technological applications. So it is the era of everything we need in terms of in a smaller space. Smaller. In the semiconductor industry, this translates or relates faster. How much small you go, so that much of faster and speedy performance we can expect. So as I said in the previous slide, the quantum effects that actually define the nano semiconductors. So these are the three important quantum effects. One is quantum confinement. Very soon in the next session, as I said, will be delivered and explained, discussed by Dr. Ravi. And quantum tunneling, we know that. So quantum confinement means when the electrons are restricted within the nanoscale species, their energy levels become discrete and become rather than continuous. This quantum confinement creates a lot of dramatic changes in the electronic and optical properties compared to their bulk behavior. So we know that we can expect quantum tunneling, so that is which is highly not possible in case of classical mechanics. In the quantum tunneling means we can expect electron can pass through some energy barriers that would possible in the quantum effects. And even we can expect size dependent behavior in the nano semiconductors. Even optical property, that is the color emission by the nano semiconductors, entirely different, and we can tune the nano semiconductors. Different sizes of nano semiconductors exhibit show different emission of colors. Even we can expect tunable electrical conductivity. Even we can tune so desired electrical property, and also other properties can be precisely tuned by simply changing the size of the nanosemiconductors. So this phenomenon is highly, it is not possible in the conventional semiconductors. This is possible in case of only in the nanosemiconductors. So these are some different types of nano semiconductors. So where we are familiar, there is the first type is quantum dots, and the second one is nano wires, and the third one is 2D nano semiconductor materials. What exactly quantum dot means? So these are the quantum confinement. If you take in all the 3 dimensions, we may expect 0-dimensional semiconductors having discrete energy levels that is about 2 to 10 nanometer, and they emit the specific colors based on their different sizes. So this kind of quantum dots are widely used in display technologies, medical imaging, biosensing applications. In these case, we are using these quantum dots. So that name itself indicates that 0 dimension means a bulk material. If you are having a bulk material that is 3-dimensional, if you confine in all the 3 dimensions, we go to a point, or we can reach up to a dot. In that sense, we call it as a quantum dot. And another one is if the 2 dimensions are confined, so we left with 1 dimension. So we may expect that is a wire shaped in the nanoscale. Hence, the another type of nano semiconductor is called as nanowires, where 1 dimension is very in terms of micrometers, whereas the diameter of this such wires it is of the order of 1 to 100 nanometer. Hence, this is also called as nano semiconductor that is in the form of wire, or even we can say nano rods. So these are this kind of some nano semiconductors ideal for ultra sensitive sensors, and even they can be used or applied in case of next generation transistors. And another classification of nano semiconductor is 2D material with unique electrical properties. For example, to mention 1 layered and 2 layers carbon nanotubes, molybdenum sulfide with having unique and extraordinary electrical properties. Other than this, other than the quantum dots, even we may expect core shell nanoparticles, where in order to enhance the stability and chemical resistance and their functionality and performance, so the quantum dots or nanoparticles are covered or layered by some sophisticated structures, so which enhance their properties, optical properties, very dramatically. So these sophisticated layer structures combining different semiconducting materials, thereby the core provides optical properties, or it is a reason for emission of optical properties, where the shell enhances its stability and chemical resistance, and also their functionality enhances. So next, come to why we need these nano semiconductors. So we are having a lot of semiconductors with lot of applications and advancement in semiconductors. Still, is it necessary having these nano semiconductors? The answer is absolutely right. So these are some of the important points I would like to highlight why the nano semiconductors is very much necessary in this era of modern age. First one, the important one is, so we are familiar with this. So as engineers, we know that this Moore's law. All engineers, we are familiar with this Moore's law. So what exactly Moore's law means? So before that, so what exactly Gordon Moore stated that, so in order to enhance the performance of a computer, that is any computing machine or computing system, so we need a lot of transistors. So where he surveyed around 50 to 60 years survey, with respect to semiconductor industries, where he approximately stated that, so every year the number of transistors, every year doubles. That is, every 2 years, the number of requirement of transistors to enhance the speed of computing machines is doubling. So this is what the Moore's law. So earlier days, we know that to run a computing machine, we need a lot of space in terms of rooms or classroom sizes, So we need to stack all the transistors. We need to connect them in, properly electrically. So there's a lot of, complicated work to run a simple computing machines in the earlier days, that is in the 1820s. So this was the pick, Charles Babbage, he created difference engine, that is, computing machine. So basic computing machines, he, stacked all the transistors in a room, so to run a simple computing machines. So in the late 19s, that is 1972, Intel company had 3,500 transistors. So in order to have the speed, just imagine 800 kilohertz, that is 0.8 megahertz, the rate at which the processor completes processing the cycles. So this much number of transistors was needed to run a computing machine, that is computer chip. So after 2 years, the same company released another processor that is having 4500 transistors where they have reached 0.8 megahertz speed to, that is 2 megahertz speed. So in order to enhance the speed and performance of any computing machines, the number of transistors also go on increases. So from 3500 to 4000. Next 4 years later, there was even bigger jump. That is, the same company had whopping 29,000 transistors and initial clock speed of, that is, they have reached from 2 megahertz to 5 megahertz. That is how, as the number of transistor go on increases, the speed, that is performance of the speed of the machine, that is computing machine, go on and gradually increases. In just few years, the number of transistors go exponentially and the processing power made huge jumps, just as Moore's law. This was predicted. This kind of statistics was first studied and observed by Moore, and finally he stated in the year 1965 that the number of transistors, that is he predicted that the number of, as the number of transistors rate increases exponentially, similarly the performance rate also go on increases. The computer industry has followed this prediction since then, and he plotted this observation, that is this his survey over the 50 years. This is how it looks. He plotted since 1972 till 2020, where he predicted. So every year, every 2 years, the number of transistors, this is the y-axis, represents transistor numbers on a per chip, that is in a microchip, and this one years. So he finally concluded and he stated the number of transistor on a microchip. Microchip means this one, this kind of microchip, he stated, roughly doubles every 2 years in order to enhance the performance and the speedness of the computation of a computer. This was a prediction done by Moore's law, and this is on a small chip, that is the semiconductor chip. So the number of transistors, that is, as the number of transistors increases, the speed, that is performance and speed of the computer increases. And the next question comes, how long this Moore's law continues to hold? What are the ultimate limitations? Do you have any limitations? Because everything we need very quick, everything we need, the performance is in the best way, everything we need in a speedy way. So all this happens only because of, as the number of transistor has to increase in the microchip. So if the number of transistor go on increases, what about the lot of physical limits we may come across? Even we can may reach economical limitations also come into exist. So in the year, if you take the research, that is observation, in the year 2021, the semiconductor size, that is the data size, has reached 5 nanometer node. This was the data in the 2021. Right now, so that is after 5 nanometer node, that is process node on a microchip, that is 5 nanometer node means it is a point where we can put the data, that is in the 5 nanometer size. So this was entered a mass production in the year 2020s and 21. Later, the semiconductor, that is Taiwan Semiconducting Manufacture Company, that is private company, that in that industry they have moved from 5 nanometer to to 3 nanometer. That is right now they have achieved, instead of 5 nanometer, they go smaller size, that is they have reached 3 nanometer, and is currently they are tracking for, they are researching, that is in order to still they wanted to reduce the size of the chips, that is to the limit, that is 2 nanometer. So because of this Moore's law prediction, that is the number of transistor growth has to exponentially increases in order to enhance the performance or speed of this one. But there is a physical limitations and economical limitations has in the Moore's law. So therefore we have to end this because of these physical limitations and economic limitations. And next, what is the next alternate options for this one? The alternative option is this, the quantum computation, where we are using qubits. All these qubits are made by nanosemiconductors. So in order to have the speedy performance, everything the best performance, we have to use, instead of this now transistor, the traditional transistors, we can use qubits. The quantum computation is the era now, so where we are using the qubits for the computational purpose. So these qubits are made by nanosemiconductors. Because of this reason, we need lot of we need this nanosemiconductors. So another the need of, that is necessity of nanosemiconductors is, as I said, everything we need smaller, faster, and energy efficient devices. That is the need of necessary of this modern era. Because of this reason, everything we need in nano, that is in a smaller size, and it should be faster, and it should be energy efficient. Any device you made or any device you manufacture, so these criteria should meet. So these are the criteria, are meeting by this, nano semiconductors. This is the reason why we need these nano semiconductors. Another reason is, so there is a lot of limitations and constraints while scaling the bulk materials, traditional scaling, that is, bulk materials. So hence we need these nano semiconductors where we have, quantum effects at the nanoscale. So nano semiconductors enhance, as I said, increase speed. That is, in a smaller size we can, put a lot of things. That is, smaller compounds mean shorter distances for electrical signals to travel, resulting in a faster processing. How the speed increases means because of as the distance becomes shorter and shorter, so the electrical signal can easily travel. That is in a pass, resulting the process in the faster processing in the microchip. So electrical engineers and computer science engineers may understand how this the chip microprocessor and micro the processing things happens. So thereby we can have improved device performance by using the nano semiconductors. And these nano semiconductors uses low power consumption. As I said, so when you go quantum confinement effects, they exhibit unique, extraordinary electrical properties with reduced leakage currents, and they need lower power consumption compared to the bulk materials, contributing more energy efficient electronics and longer battery life for portable devices. Another important reason is, so especially nano semiconductor means, so we need everything that is, thermally stable semiconductors. So especially the single walled and double walled carbon nanotubes have this kind of improved thermal conducting properties, so which are crucial for efficient heat dissipation in high performance electronics to prevent overheating and ensure reliability. And another important reason we using the that is nano semiconductor is, because of its unique properties. At the nanoscale, as I said, they exhibit novel and unique physical, optical, and chemical properties due to quantum confinement effect. And this allows for the tuning properties, like we can tune or we can engineer its band gaps in case of quantum dots. For example, to mention in quantum dots, if you tune the band gap, we can expect different kinds of applications in optoelectronics, especially in display technology, that is light emission technology. So for different sizes, we have different optical properties. So thereby we can use them for LEDs, even solar cell and display purposes. So these are some important, I have not mentioned all, but some important reasons why we need these nano semiconductors. Next, I would like to highlight how the nano semiconductors can be synthesized. So broadly speaking, any nanomaterials or any nanostructure can be synthesized by two methods. There is two techniques. One is called top-down method, and another one is called bottom-up method. So every engineers or every scientist are familiar with this kind of methods or techniques to synthesize the nano semiconductors. So here in the top-down, why this method is called top-down method means because that name itself indicates that top means we have bulk material. This is the bulk material. So from which you want to synthesize nano semiconductors. First, you take the bulk material. Then, by various techniques, we have a lot of enormous amount of techniques or methods to make this bulk material into nano semiconductors. So I will be touching some important methods of techniques by which we can synthesize. Then this bulk material made into powder. Then finally powder fabricated, that is synthesized into nano semiconductors. So this is why it is called top down means first we take the top, that is bulk material, then made it to powder by various techniques I will be touching very soon, and finally we have nano semiconductors. So this is from top to down method. Whereas in the other method, that is bottom up method. Why it is called bottom up method? Because basically here we consider atoms or molecules which are very smaller size. Then we made them by using various techniques as a clusters, and thereby finally we have nano semiconductors. So this is bottom to up and this is top to down. So hence these are the two techniques by which we can synthesize the nano materials, that is nano semiconductors. So these are some important fabrication techniques by which we can synthesize the nano semiconductors. As I said, in the top-down methods, starting with bulk materials, and finally we have the nanoscale materials. In the bottom up methods, we have building the nanostructures by atom, that is using atom by atom or molecule by molecule. So in order to have this fabrication techniques, here I have mentioned some important fabrication techniques both in top down and bottom up methods. In that, I would like to mention the first one is photolithography. Photolithography means we are using the light to pattern the semiconductor vapors. I will just show here what exactly this technique means. Photolithographic process means that name itself indicates that here we are using photo, that is light. Lithography means in order to have the vapors, that is semiconductor vapors. So here we have mask. Here we are allowing the light to fall on the substrate. So here we have silicon substrate. Above that we have silicon oxide layer. Above that we have some photo, that is photo blocking resistant material, photoresistant material. So this kind of substrate, if you expose this material, this coating to the light, that is photo, what it does, so wherever photoresistant, that is mask, is there, it is not allowing the light to pass on the substrate. That is wherever we have some gaps where we have the photolithographic process is taking place, both negatives and positives. So by that we have the semiconductor vapors in the nanoscale. The precision fabrication techniques enables to tailor the band gap, conductivity, and optical properties for specific applications, especially from ultra efficient solar cell to quantum computing components. So this is photolithographic process by which we can prepare the semiconductor vapors. And another technique is electron beam. Another technique is electron beam lithography. Only difference is here we are using photo, and in this method we are using, in place of photo, that is in place of light, we are using electron beam. That's all. So here in place of light we use electron beam to manufacture or to fabricate the nano semiconductors. So that method is called electron beam, that is electron beam lithography. So where focused electron beams create the ultra fine features. And another technique that is in the top-down method, that is called etching techniques. So that name itself indicates that we can etch the material chemically or plasma removal material layers. So this is our, I will show one sample here. So here, look at this. This is, broadly speaking, in the etching techniques, we have two types of etching. One is wet etching and another one is dry etching. So in the wet etching method, what exactly we do? So which material you want to prepare, that is, vapors, you just, take that material and put it in the chemical. This is the etching solution. So this is the etching solution. And in which portion, if you don't want to etch, you just, take the mask and put it like this. So wherever the, there is no mask, here, you can expect the etching portions. So these are the, workpiece. This is the etching portion by chemically. This one. So whatever the desired for, size or shape you need, you can mask it, and accordingly you can put it in the etching solution. So chemically it etches in the desired semiconductor vapors. And in the dry etching process, what it does, so they will just simply hit the radicals on the substrates. So where we can expect this kind of etching in the dry etching. In the another one is, even we can use inert ions to etch the working piece material. Even you can use both physical and chemical process in order to have the etching techniques. So this is etching technique by which we can have the vapors. And another important technique, mechanical milling. That is, by using mechanical process, we can synthesize the nanoparticles or nano semiconductors. So what exactly in the milling process, we are familiar with milling machines and all that. So there are variety of millings we can expect. So here a tray or mill, so where we place the materials which you want to synthesize nanoparticles. Here you just turn it and it will start processing of milling this bulk material into fine nanoparticles. And even we have pan mill, and put the bulk material here, and just take the pan mill, turn on the pan mill, it will crush that bulk material into nanoparticles. Even we have roll mill. In the roll between the two ball mill machines, if you place the bulk material here, it will crush that material into nanoparticles. Even we have tumbler ball mill. You just take the sample, and like this, if you ball milling method, we can expect the product synthesis of or fabrication of nanoparticles. Even we have vibratory mill. Just vibration of this mill, we can expect crushing of the bulk material into nanoparticles. And another one is planetary mill. That is by placing the planetary mill, we can bulk material into nanoparticles we can expect. These are the some important some important top-down methods by which we can synthesize the nano semiconductors. And whereas in the bottom of methods, where, as I said, building of nanostructures from atom by atom methods. So here I have mentioned some important techniques which are widely used in the synthesis of nano semiconductors or in the fabrication process. One is CVD, that is chemical vapor deposition. This is chemical vapor deposition technique, where, as that name itself indicates that, so this is the gas-based synthesis. So which material you want to synthesize, material that you take into the gas in the as a precursor, in the gas form, you just put it here, and as the gas goes on here, because of heating zone, in the heating zone it vaporizes and all the chemical vapors deposited on the substrate. So film deposition, and this is the nano semiconductor. This is how a simple technique by which we can prepare the nano semiconductor films. And another method is molecular beam epitaxy. So all this kind of details will be touched and discussed in detail in the coming sessions. Especially this kind of fabrication techniques will be detailed in the day 3 session 5. That is advanced fabrication methods. That is molecular beam epitaxy, CVD method, atomic layer deposition methods, and all that. So here I would like to just touch and not in detail about the technicalities, just how the process happens. I'll just touch here. So in the molecular beam tech epitaxy, as that name itself indicates that, so here different molecules, if you want to build up on the substrate, you take this one. Efficient cells means it is just like a gun like shaped cells, so by which the molecules can be thrown or fire at the substrate. So thereby we can expect layers of atoms build up on the substrate. So by controlling the substrate heat and all that. So this is the film by which we have developed using the molecular beam epitaxy. And another important widely used technique is hydrothermal process. It is the simplest one, where, as that name itself indicates, that it uses hydro means aqueous medium, thermal means the treatment of heat. So here I have shown one simple technique, that is how PAP nanorods have been synthesized. So the materials, that is a precursors material adding to this one under NaOH and under the condition that is pH at 10. So thereby precipitation takes place. So this precipitation subjected for hydrothermal treatment. Hydrothermal treatment means using high pressure and temperature, appropriate temperature conditions. Thereby this precipitate is converted into nanorod shaped, that is nano-sized shape like this. This is how the nanorods, especially one-dimensional nano semiconductor materials, will be synthesized with the help of this simple technique, that is hydrothermal treatment. And another one is solution phase. Another one is solution phase synthesize. So I have not taken that picture. And the last one is self-assembly synthesis. Self-assembly means, so that word itself indicates that, so the molecules self-assemble because of their force of attraction due to weak force, that is van der Waals force or covalent force and all that. So there are two types of self-assembly techniques. One is static, another one is dynamic. So as that name static means, so there are for example co-assembly techniques. Suppose if you have two different materials like this, one is red colored and one is black colored. In the co-assembly method, what happens, because of their weak interaction, intermolecular forces or interatomic forces, that is van der Waals force and all that, they started to assemble nearby them like this. So all one type of atoms or molecules go one side, and other type of like they are moving aside. That is, they are assembling without any external agency or without any external aid. They assemble like this. Or if you allow the for the sufficient time, even we may expect this kind of self assembly, that is co-assembly techniques. So hence co-assembly means themselves they will arrange or assemble in the solution phase. And another one is hierarchical self-assembly. Hierarchy means based on the size, that is short range, based on the interaction type of the force. Van der Waals force, based on the range, we we have this kind of different assembly structures. For example, in the interaction one, that is, if the force, that is weak force, is very short, under this condition, we may expect this kind of small assembly nano semiconductors. In this, that is in the medium range, that is if the force of attraction between the two atoms or molecules is in the medium range, then we may expect this kind of assembly, self assembly nano semiconductors. If the interaction force between the atoms is very long range, then we may expect this kind of self assembly in the hierarchical order. This is another method. And another one, we have directed self assembly. Directed means, suppose if you have if a sample is characterized by positive and negative ions, where we have some positive host and negative zone regions, thereby you can direct the negative, that is by simply allowing them to interact, thereby they can direct with the positive host. This kind of directed self assembly nano semiconductors we may expect. So this is what the traditional methods are being used in the semiconductor, that is nano semiconductor synthesis. There are the fabrication techniques. Even right in the what exactly the present era is going on, that is especially Taiwan semiconductor manufacturer, what they are thinking is, so they are using all the technologies, that is present yet technology, to synthesize the semiconductors. For example, nowadays we are in the era of sophisticated technology and high advancement technology. With the help of technology, they can precisely and whatever the desired shape of nano semiconductors, we can go for that synthesis. So one such the technique I would like to highlight here. So nowadays, this is the era of technology. With a technology, they are synthesizing nano semiconductors. That is AI-driven optimization, where machine learning algorithm, using with the help of machine learning algorithms, they can predict where defects actually happens, they occur, and thereby they can optimize the manufacturing process or synthesis process in real time, and dramatically accelerate the chip production cycles. So in the traditional methods, we don't have this kind of prediction, but AI driven algorithms that can predict where exactly something is going wrong, where exactly we can find the defects, where exactly the mistakes is going to happen. So this kind of predictions will be done by machine learning algorithms, so thereby we can optimize the synthesis process of nano semiconductors with the help of technology. This is the technology is being used now, right now. And another one is extreme ultraviolet lithography. This way, because we heard about photolithography and electron beam lithography and all that, and this one is another technology they are using, that is extreme ultraviolet lithography, so which enables precise patterning at atomic scales. So this preciseness at atomic scales we don't have in the traditional methods of fabrication techniques. So this technique enables the precise patterning of atomic scales using light wavelengths of just 13 nanometer to create the interactive circuit patterns. So in the semiconductor chips or semiconductor industries, in order to have the circuit patterns, they are using this kind of technique, that is lithography, using ultraviolet lithography technique with the help of ultraviolet light. And another important technology they are using, that is automated excellence. So right now we have we are in the era of automation and robotics. Advanced automation reduces human errors and thereby improving manufacturing yields and shortens the innovation cycles from the concept to production. So these are the some cutting edge technology they are being used in the manufacture of nano semiconductors right now. So once the synthesis is done, how to characterize them, that is how to identify them whether they are in the nano size or not. So here we have a lot of the characterization techniques in order to confirm the semiconductors whether it is in the nano range or not, or its in terms of composition or elemental analysis. We have a lot of techniques. Here I would like to just mention, not in the not technical aspects, just would like to mention what all characterization techniques we are using to confirm the nano size semiconductors. So this kind of different techniques will be discussed in the various different sessions in the coming 6 days by different experts. So we have this broadly speaking, we have a lot of characterization techniques. So to mention, we characterize different types of characterization techniques. One is optical, that is optical probe characterization techniques. Also we called it as imaging. So where this characterization techniques aims to characterize the nano semiconductor in terms of image. And another one is electron probe characterization techniques. So we'll go one by one in detail. And another technique is scanning probe characterization techniques. So next one is photon, that is spectroscopic probe characterization technique. We're using UV and fluorescence technique. Using, pardon?
Google link for feedback create ಮಾಡಬೇಕು ಸೆಕೆಂಡ್ ಸೆಷನ್ ಆಗಾದ್ಮೇಲೆ ವಾಟ್ಸ್ಆಪ್ ಗ್ರೂಪ್ ಅಲ್ಲಿ ಹಾಕ್ಬಿಡ್ಬೇಕು.
Create on ಮಾಡಿನ.
Sanayaka sir, can you mute yourself? Sorry. Okay. So another type is ion particle probe characterization techniques, and another one is thermodynamic characterization, where we can decide the thermal stability of nanosemiconductors. The first one is, as I said, optical, that is, or imaging probe characterization techniques. So again, here in this category, we have a lot of techniques to characterize the nanosemiconductors. The first one is confocal laser scanning microscopic. With the help of this one, we can take the image or ultrafine morphology of the nanosemiconductors. Thereby, we can study how exactly the morphology or topology of a nanosemiconductors. And another important technique, another one in the imaging, that is scanning near field optical microscopy. That is, a rastered images we can get by this, by technique we can get the rastered images. And another one is two photon fluorescence microscopy, where fluorophores and biological systems can be characterized with the help of these techniques. And another important widely used technique, that is, dynamic light scattering, where we can precisely uh, uh, measure the particle size with the help of dynamic light scattering technique. And another one is Brewster angle microscopy. So this is preferably for gas liquid interface imaging. So where if we have the nanosemiconductor in the form of gas liquid interface, we can use this kind of techniques in order to get the image. So another important technique, that is electron probe characterization techniques. Again, we have a lot of characterization techniques under this category. The first one and mostly used is SEM, that is scanning electron microscopy, where we can get the raster image or topology or morphology of a nanosemiconductors. And another one is electron probe micro analysis. Thereby we can measure the particle size, even local, we can analyze the chemicals, that is local chemical analysis we can help of EPMA technique. And another one widely used technique is transmission electron microscopy, whereby we can get the image and particle, and even we can decide shape of the nanosemiconductors. And another one, that is high resolution transmission electron microscope. That is, we can get the image, that is structure and chemical analysis we can done with the help of this technique. And another one, that is scanning transmission electron microscopy. So it is preferably used for biological sample if the nanosemiconductor in the form of biological sample. So this kind of technique will be touched by Dr. Sannayakar in the last day. So maybe the interface of this bio with nano. So he will be touching or discussing with this this technique. And another one is low energy electron diffraction. That is, thereby we can use it for surface and absorbate bonding analysis. Another one, electron energy loss spectroscopy, that is in order to analyze the inelastic electron interactions. If we are having any inelastic electron interactions, we can study this inelastic electron interaction with the help of this technique. And another important technique, that is agar electron microscopy, so where chemical surface analysis can be done with the help of these techniques. So most widely used, that is scanning probe characterization, as that name itself indicates. So we can scan the nanosemiconductors, thereby we can get a lot of characterizations. So another in that, one of the important technique is, that is we are using, that is AFM, that is atomic force microscopy, where we can get the topology, even image and surface structure of the nanosemiconducting material. And another one is chemical force microscopy, where we can study the chemical and surface analysis of the sample. And if the nano semiconductors are in magnetic nature, so then we have to use this technique, that is magnetic force microscopy, where we are using, if the nano semiconductor magnetic property or magnetic characterization, we can analyze with the help of this technology. And another one is scanning, that is STM, that is scanning tunneling microscopy. Again, it is used for topology, imaging, or surface structure analysis. Another one is atomic probe microscopy. So here we can get, with this technology, we can get the three-dimensional imaging. Field ion microscopy for chemical profiles and atomic spacing. And another one is atomic probe tomography. Thereby we can position sensitive lateral location of atoms. So location of atoms can be studied by with the help of this technology. So another important technique, that is spectroscopic probe characterization techniques, where we are using various fluorescence, UV visible, and all that techniques in order to characterize the nanosemiconductors. One is called UPS, that is ultraviolet photo emission spectroscopy, in order to analyze the surface of the nanosemiconductors. And another technique is UV visible spectroscopy, widely used by all the researchers and engineers and scientists for the chemical analysis. Thereby, they can decide the band gap. That is, they can engineer the band gap. Even another technique, that is atomic absorption spectroscopy, that is for the chemical analysis. And another one is industrially coupled plasma spectroscopy for the elemental analysis. And another widely used technique, that is fluorescence spectroscopy for the elemental analysis, and localized surface plasma resonance for nano-size particle analysis. So these are the various techniques by which we can uh, probe the nanosemiconductors or characterize the nanosemiconductors with the help of spectroscopy. These are the another ion particle probe characterization techniques. That is, the first one is Rutherford backscattering for the quantitative and qualitative elemental analysis, and the next one is small angle neutron scattering for surface characterization. Nuclear reaction analysis for depth profiling of solid thin films, especially nanosemiconductors if you're having in the solid phase. So this technique can be very helpful. And we know that Raman spectroscopy for the vibrational analysis, XRD for the crystal structure analysis. Thereby even we can decide the size of the particles with the help of XRD pattern. And one of the important technique for the element analysis widely used is energy dispersive X-ray spectroscopy, whereby we can decide which kind of element or which kind of electric chemical composition is there in the sample. So this is the EDX methods. We can easily analyze all the elements present in the sample. Another one is small angle X-ray scattering. Thereby we can analyze the surface, and even we can if the particle sizing also can be measured. And another important technique, that is cathodoluminescence. Characteristics emission of the cathode, that is electrons, can be analyzed with the help of cathodoluminescence. And NMR, widely used another method for the analysis of nuclear species. So in order to study the thermal stability nature, that is how much our nanosemiconductors are thermally stable, in order to characterize the those thermal stability of nanosemiconductors, we are using TCA, DTA. These are the two important widely, that is another one DSC. So these three techniques have been used in order to analyze how thermally stable the nanosemiconductors are. By the first technique, we can analyze how much mass loss versus temperature. If you supply the temperature for a nanosemiconductor, at what temperature it is losing its mass. So that kind of analysis we can study with the help of TCA. And reaction heats and heat capacity can be studied by DTA. And reaction, that is phase, how the phase, the phase of the nanosemiconductor, how it changes, that can be studied by DSC. And latent heat of fusions can be studied by nanocalorimetry. And surface area analysis done by BET, that is Bernier Emmett Taylor method. And another important method is the CS method, that is colloidal size and specific surface area can be studied. So these are the summary of the classification of characterization techniques. For structural characterization, we go for XRD, TEM, SE, SAED, whereby we can get the information about crystallinity and lattice spacing. And for morphological characterization, we use scanning electron microscopy, AFM, and TEM. Thereby, we can decide the shape of the nanosemiconductor. Even we can measure precise, the size of the nanosemiconductor. Even we can, analyze the surface feature. And optical characterization will be done by UV visible, fluorescence, and Raman spectroscopy. So, in order to get the information about band gap and optical transitions. In order to have the composition, that is elemental analysis, can be done by EDX, XPS, and EAS methods, where thereby we can get the information about elemental composition and oxidation states. In order to have the electrical properties, so can you mute, madam? Sorry. Hello.
Go ahead, sir.
Sorry.
Yes, sir.
For electrical properties, that is, electrical properties of nanosemiconductors can be studied by techniques called probe method and Hall effect. Thereby, we can get the information about the resistivity, that is electrical conductivity. Even we can study about the carrier mobility. And vibrational studies done by FTR and Raman techniques. Thereby we can get the information about how exactly bonding between the nano, in the nano semiconductors. Even we can analyze the chemical structure. So the last part of this, the talk is about the applications of these nano semiconductors. So we know that the nano semiconductors have entered, changed dramatically in the modern era. So where and the nano semiconductors are widely used in almost all fields of science and technology. So here I have mentioned some important, the fields are areas where they are being used widely in the modern era. The first one, so the nano semiconductors are widely used in the advanced electronics, where nanoscale, you heard about nanoscale transistors like FinFETs, GAA-FETs. So they continue pushing Moore's law forward. So we discussed about in detail about Moore's law, how exactly so the Moore's law predicts, the prediction of the number of transistors over the years. So this Moore law can be forward by using this kind of nanoscale transistors made by the nanosemiconductors. So thereby enabling more powerful processors in the smaller package with reduced power consumption. So as I said, everything we need in a smaller space with a smarter, speedy, and efficient performances. So this can be achieved or this can be done by using the nanosemiconductors. And the second one is we are using this nanosemiconductor in the energy harvesting applications. To mention, we are using this, for example, quantum dots in the solar cells in order to enhance the absorption rate. So what we have traditional solar cells, so the absorption, in order to increase the absorption, that is enhanced absorption. So if you, along with the solar cells, if you use the quantum, that is nanosemiconductors or quantum dots, so definitely we can achieve higher efficiency by capturing broader light spectrums. So then even nanosensors embedded in the energy systems provide real-time monitoring and optimization. So this is in the energy harvesting, the most of the nanosemiconductors play an important, that is vital role in the energy harvesting systems. And another important area where the nanosemiconductors are widely used in the optoelectronics. So as I said, so these quantum dots and all that are widely used in the display technology. For example, to mention the quantum dots LEDs. So we have light emitting diodes so deliver different colors with accuracy and vibrancy. So with a 40% of lower power consumption compared to the traditional lights or traditional light emitting devices. So because of this high efficient electrical and optical properties, so they are being widely used in the traditional displays. So thereby they bring some revolutionary technology in the TVs, smartphones, and even virtual reality headsets. And they also widely used in the medical field as a biosensors. So this will be detailed by again in the last session of Dr. Sannaikar maybe. So bio nano interfaces. So where semiconductor nanoparticles, they are using, used for drug delivery, bioimaging, DNA sequencing, cellular process, and variety of applications in the medical fields using with the help of these, nanosemiconductors. So real world impact, that is, so to mention some important applications. So as I said, quantum dot displays have come into, place in the traditional displays with the help of, nano semiconductors. So they are being used delivering 100% color volume and over billion distinct colors, transforming entertainment of the professional and creative work. So we are in the era of black and white, then color TV, then HD, then 4K and all that. So this advancement, it is mainly because of nano semiconductors are being used in the display technologies. So nano semiconductors uses in the FinFETs. So every modern CPU and GPU uses this, FETs, that is FinFETs architectures at the scale of the 7 nanometers and even smaller nodes. As I said, even we have reached up to 3 nanometer nodes. So because of the, their unique electrical properties at the nanoscale, the power leakage is very small. That is about 50%. So thereby, and also another advantage is they are doubling the performance. They are increasing the performance rate of the computation, that is computing machines, enabling everything from smartphones to data centers. That is another important real world impact of this nano semiconductors in the this technology, that is computing field. Small solar monitoring, as already discussed, that is in the solar cell. If we are adding quantum dots, so we can enhance the absorption capacity. Thereby, we can enhance the efficiency of this the conversion of light energy into electrical energy. So medical imaging breakthroughs, as I said, it can be used for drug delivery, DNA sequencing, cellular process, and all that. Even nowadays, the right now the nanosemi using with the help of semiconductors. So there is especially quantum dots, that is semiconductor quantum dots enable targeted cancer cell imaging with precision and lighting up tumors while remaining invisible to healthy tissues. So where they are not disturbing any health tissues, only they destroy the cancer attacked cells with the help of medical imaging breakthroughs. So the semiconductors are widely used in the different atomic in the quantum and atomic scale, that is semiconductor devices. So here we have single atom transistor right now. So they are, as I said, the qubits. Individual atoms serve as a transistors with a donor spin qubits in silicon, creating a foundation for scalable quantum computing architectures. So we are using single atom transistor as a qubits now. So with the help of nanosemiconductors. Another one is photon based lithography and electron beam manipulation emerge as a disruptive methods for atomic precision manufacturing. And even they are trying, that is the next future era is to try the 3D qubit structures. That is roadmap includes three-dimensional qubit architectures and exploration of new impurity species for enhanced quantum control and coherence. So we can conclude we are no longer just making chips smaller, we are engineering devices at quantum level, where the rules of classical physics give our way to the new era of, that is quantum effects, and that is quantum mechanics ruled by quantum physics. So now how this nano semiconductors are being in the present technology, that is small from smartphones to AI and even beyond. So right now we are using 5G, that is we are in the era of 5G. Nano semiconductors enables, that is lighting up 5G network speeds. So they are powerful smartphones and seamless connectivity in our pockets now. It is all because of with the help of nano semiconductors, everything we have in the smaller size and speedy and performance is efficient. And another one is edge AI. So AI is all about remembering and giving all the things. Artificial intelligence, we are in the era of charge. We are using everything, charge GPT and everything. So that is how it works. It is all because of memory devices. So these memory devices are again made by the nano semiconductors. So that is edge AI. Intelligent devices process data locally with unprecedented speed and minimal power. By using the nano semiconductor materials, they are using as a memory devices. Another sustainable data centers, these nano semiconductors are being used. Energy efficient chips reduce carbon footprint for cloud computing. So where we are using, the energy efficient chips made by the nano semiconductors, we are using it for cloud computing and massive data operations. Even we are using this nano semiconductor in autonomous vehicles, and even we are using in self-driving cars and in electronic vehicles. And even we are having we are checking everything wearable technology, that is efficient chips power we are using smart watches which monitors our health, fitness, tracking, even walkable, that is steps tracking everything. Even it can monitor our heartbeat as well as. So all this 10 if you go back the what kind of materials they are making they are manufactured means, it is because of with the help of nano semiconductors. And IoT expansion, another technology, that is nanosemiconductor are being widely used in the IoT expansion. That is billions of connected devices become possible with ultra low power nanosemiconductor technology. So with the help of this material, that is IoT, Internet of Things, that is it is assembly of network where we have things, that is devices connected with softwares, sensors, and all that. Together we call it as IoT, where the things are being used in, that is nanosemiconductors are being used in the IoT expansion. So we can conclude nanoelectronics serves as a foundation for the next 25 years of computing and digital transformation, powering innovations we can barely imagine today. So these are the some important properties. Because of these properties, because we know that nano semiconductors have unique properties: large surface to volume ratio, enhanced charge transfer. We can tune the band gap. They have efficient absorption and adsorption properties. So because of these properties, they are widely used in the nanometers for energy storages, especially in the lithium ion batteries. So which will be detailed and discussed by Dr. Arun sir in the last day. So they are even nano semiconductors are widely used in the supercapacitor to enhance the capacitor, that is storage capacity, because of these properties. So now the last part of this talk is about what are the challenges or opportunities we are facing in the nano semiconductors. Of course.
Sir, Pujar sir, just a minute. I request the participant, somebody's mic is on. Please switch off that mic. I request. Hello. I request the participant, one of the participants' mic is on. Yes, sir. Pujar sir, please continue, sir.
Pujar sir. Sir, can you speak now? Pujar sir.
Sir, tell me.
Sir, okay, sir, go ahead, sir.
Thank you. The screen is visible. So can I confirm from anybody?
Sir, not yet.
Sir, please share it once again.
Yes, sir. Sorry. Sir, from my end, I'm unable to share my screen. I think you have done some changes with respect to technical aspect.
Okay. Sir, wait a second, I will check, sir.
Yes, sir. Right now, I'm unable to share my screen.
Okay, sir. Okay.
I think you have made some changes.
Sir, can you join once again?
Yeah.
You are there in the meeting, but I am unable to see you here.
Okay, sorry. I will just leave the meeting and I will come back. Sir, still I am unable to share my screen. Sir, you do one thing, sir. You make me as organizer and presenter. Then I can able to share my screen.
Yes, sir. Just we are checking that. Just a minute.
Yes.
Yes, is it now visible, sir?
Yes. Now I can share my screen. Thank you.
Okay, thank you, sir. Thank you.
Yes, sir.
Yes, sir. Thank you. Hope I'm audible and the display is visible.
Yes, sir. Yes, sir.
Thank you.
Yes,
So
sir.
despite of having a lot of applications and unique properties of nano semiconductors, still so there are some grand challenges, and that will open for new opportunities in the field of nano semiconductors. In that first one, so there is a challenge in fabrication technique. So with respect to its precision and the reproducibility, that is the first challenge we are facing in case of nano semiconductors. So if you are the facing the challenge with respect to fabrication and its reproducibility, that is the first one. Second one, so we know that as the size go on decreases from bulk to nano, so the lot of the thermal that is in heat dissipation takes place at nanoscale devices. So in terms of devices, we need to monitor this heat dissipation at nano. This is a great grand challenge which nano semiconductor researchers are facing. So another one is so we know that quantum is always uncertainty and its variability. So we cannot have the same the precision, so the reproducibility because of this issue. And another one challenge is, so everyone we are talking in terms of green nanotechnology, why we have to use the semiconductors. So that is another one, because we need sustainable fabrication and we need everything green nanotechnology. So these are some important grand challenges which are facing in the nano semiconductors. So as I said, heat dissipation at nanoscale, and manufacturing variability because of quantum nature, and so we have a lot of next generation materials in place of semiconductors, to mention graphene 2D materials, that is molybdenum disulfide and all that. And another big challenge, that is another opportunity, or we can say innovation, is the combination of this nanoelectronics with molecular electronics for biocompatible devices, and with spintronics for ultra low power computing, and creating entirely new class of intelligence. So if you've done this, a lot of opportunities will be open in the field of nano semiconductors. So these are the different class of another challenges or future prospects of nano semiconductors. As I said, so we can consider the environmental impact, manufacturing process, life cycle assessment, recyclability and reusability of materials. So these are some challenges or future prospects in case of nano semiconductors. So future of the future scope of in the field of nano semiconductors. So beyond silicon, complementary metal oxide semiconductor. So continued miniaturization, go, if you go smaller and smaller, so that is a fast, that is three, we have reached till today, that is 3 nanometer node using advanced materials and 3D stacking architectures. So still the road is ahead, that is we can go up to beyond beyond this 3 nanometer method. So that kind of effort is being made by Taiwan semiconductor manufacturing company. So we are using this in nano semiconductors, that is quantum computing, that is another road ahead in that is future of nano semiconductors. These nano semiconductors can be used in the field of quantum computing more widely and efficiently, because they quantum dot serve as a stable qubits for practical quantum computers. Another one, that is integration of IoT and AI with the help of nano semiconductors, which I already discussed in the previous slides. And another important is sustainable energy. So advanced nanomaterials driving next generation, that is solar cell exceeding 40% efficiency. That is the next challenge, with the help of nano semiconductors. So this is what I discussed in the previous slide. That is, Taiwan semiconductor manufacturer, that is TSMC's next target, that is future road, is to manufacture, that is groundbreaking 2 nanometer JFET. That is, they scheduled it for mass production in the year 2026. So in order to get the enhanced performance and power efficiency and circuit density. So these are the 3 fields by which they are working, and very soon they will get success, because they have reached already 3 nanometer. So they are still working for groundbreaking result, that is they can they get 2 nanometer node, that is data size. So but one big challenge here is they must manage the quantum leakage effects and thermal stability, that is at the nanoscale. And another challenge is sustainability, that is manufacturing sustainable process for mass production. So these are the nano revolution in semiconductors. semiconductors have shrunk, till today, that is 3 nanometers, and Taiwan company is looking for 2 nanometer nodes. So these are the which I already discussed. I'll just skip this. So another future of that is nano semiconductors in the field of that is quantum computing. That is because quantum dots are acting as a stable qubits for the quantum computing purpose. So these are the some largest semiconductor companies in the world. First one is Taiwan Semiconductor Manufacturing Company, Samsung, Pamlier Electronics, Intel Company, NVIDIA, that is graphics manufacturing company. So the lot of scope in the India as well in the field of semiconductors. So this is our IT Minister Ashwin G. Once he stated, India is finally took a gained leap towards getting semiconductors and display fabrication manufacturing into the country. So they are investing nearly 76,000 crores in the India to design ecosystem and semiconductor, that is a semiconductor ecosystem, and thereby manpower is being developed to cater to this industry. These are the semiconductors in India. So most of the semiconductors company belongs to Bangalore. So that's why Bangalore is called as Silicon Valley. And these are some of the references which are referred for to cover this presentation. And if you have any questions, please. Thank you for your attention.
Thank you, Dr. G.H. Pujar, sir.
Thank you, sir.
As per the suggestion, there is a 15 minutes of time for all the
Yes.
participants to discuss or put your views on this topic. You are most welcome.
Thank you, sir.
Any participants who are willing to say anything, please go ahead, come forward and say a few words.
So in the meantime, I thank organizers, ATAL FDP organizers and principal of VDIT college. And most importantly, I thank all the participants for their patience. Thank you, sir. Thank you so much.
Thank you, sir. Thank you. Let us wait. Some of the participants may ask some
Yes, sir.
questions. Let us see. Sir,
Can I
starting
stop?
from Stone Age
Can-
till quantum computing, you have covered all the things.
Thank you, sir.
And I think for an introductory session, and
Yes,
this
sir.
is very, very motivational. And on behalf of all the participants,
Yes, sir.
I must say that this is a good, pitch on which now anything can be played now. So our next speaker, my very good friend, Dr. Raviraj Kashikar is also here. And he is, waiting to join with his presentation.
Yes.
And definitely one of the participant is asking for PPTs. And I would like to say that we are uploading all these PPTs on our YouTube channel, and definitely our YouTube channel will be shared, sir. And at the same time, I also request Pujar sir, if sir,
Yes,
you
sir.
have to share your PPT, sir, is
Definitely,
very
sir.
much requirement. Huh, sir?
Yes, sir. Definitely, sir. I will share it.
Please, sir. Please, sir. Please, sir.
So I would like to mention one more thing, because
Yes.
whatever I touched in the introductory part will be detailed and discussed in detail by all the remaining experts in the 6 days FDP. As I mentioned, quantum. I talked about quantum compound, band gap engineering, and all that will be discussed very soon in the next session. That is Dr. Ravi, and all the fabrication techniques will be delivered in the day 3. And lithographic and all that Dr. Rapik will be discussing, and the intersection of bio with nano will be delivered by Sannaikar, and all whatever the topics I covered in the introduction, so will be detailed in can be discussed in the later sessions. Thank you, sir.
Definitely, sir. Definitely. Thank you very much, sir. Thank you. It was a beautiful presentation. And I guess students, participants are there, and On behalf
Can I
of all
stop
of
sharing,
them,
sir?
yes, sir, you can stop sharing. No
Thank you.
issues, sir. No issues.
So still we have
And
time, 5-10 minutes. If anybody has any doubts or any questions,
yes, sir. Yes, sir.
I'm happy
And
to answer.
at this moment, I also request all our participants to just you know switch on their video so that we can take one photo, please.
Yes, sir.
All the 70 participants, including the speaker, sir.
Yes, sir. I have shared.
Please switch on. Yes, sir. I request all the participants to switch on their videos.
Sir, I'm audible, sir.
Yes, sir. Yes, sir. You are.
So I'm asking one question regarding the surface defect, sir. So it means you are discussing all the advanced microscopy techniques. So
Yes,
how
sir.
it will reveal the surface defects in a nanostructure, sir?
You are asking about how to detect surface defects with the help of techniques.
With the help of like TM, AFM.
Yeah, yeah.
Yes, sir.
Just to, I would like to mention, sir. For example, if you
Yes.
have in a sample surface defect, for example, I use a technique called XRD.
Yes, sir.
XRD. They mention just take a simple example of XRD. Suppose if the
Yes, sir.
sample is pure, we have some pattern of XRD. Sir. Suppose if it
Yes,
is
sir.
purely crystalline, imagine if it is pure
Yes, sir.
crystal. So we are having perfect crystal nature of the peaks we can expect in the XRD pattern. In that sample, suppose if you have defects other than any sample, if you are having any other defects, so take the same sample and go for the XRD. You will not you compare the original sample of without defects and this defect, you will find a lot of change in the the peaks in the XRD peaks. That is how we can analyze there is some defects in the sample. This is one simple technique, that is XRD technique, we can detect.
Yes, sir. Okay. Thank you so much, sir.
So thank you.
Thank you, sir.
Thank you, Poojar sir. Thank you
Yes,
for your insightful and engaging presentation. And really, we are truly appreciate the time and effort you have put into sharing your knowledge with us today. Thank you, sir.
thank you, sir. Thank you. Thank you, all the organizers, sir, and your principal, sir, and AICT for giving me this opportunity to share my knowledge with all the participants.
Thank you, sir. Thank you so much. Thank you.
Thank you, sir. Thank you.
Okay, sir. Okay, okay. Dear participants, you can go and have a cup of tea now. At exactly 8 o'clock, our next section will begin. I hope is it okay to all of you?
Okay, sir.
Okay,
Sir,
sir.
okay.
Yes, sir. Exactly 8 o'clock, we will begin our next session, sir.
Sure, sir.
Sure, sir.
Yes, sure. Thank you, sir. Thank you so much.
Sure, sir.
Thank
See
you.
you in next session, chair.
So in the meantime, can I say hi to Dr. Ravi? Ravi, if Ravi is there.
Ravi, sir.
Hi, everyone. How are you?
Yeah, fine, fine, fine.
Uh,
Can you show your face? So because
yeah,
we have seen for a long time.
Wait a second. Wait a second. I will show you. Yes, I'm here with the aging.
Yes.
Okay, hi. Yes.
Nice to see you.
Nice to see you, everyone, digitally.
After a long time, we are seeing your face. Thank you.
Thank you. Yeah, I also saw. I thought you were somewhere foreign. But looking at your background, I thought like you're sitting because the light is coming. So I thought you might be in Europe or USA. Then I realized it's a background.
No, I'm just using official background. That's all.
Yeah. Great, great. Anyway, how are you? How the things are going on?
Yeah, fine. Everything is fine. Your side?
Yeah, then I joined late half. You put a lot of effort to make a PPT, right? So yes, hopefully you will see at least half of my talk then to make
Yes.
a repay. Okay.
Yeah. I have just the introduction part. That's all.
Okay, fine. Thank you.
Yes. Thank you.
Yes, sir. Okay, sir.
See you then.
See you.
Right, sir. Right. See you. Ravi sir, you can share your presentation, sir, now. Ravi sir, shall we start, sir, now?
Yes, sir, we can start.
Yes, sir, you can share your PPT, sir.
Sure.
Yes, sir, it is visible.
Yeah, thank you.
Yes, sir, fantastic.
I just changed my title. I just added one more line into that. I
Yes,
hope
sir,
it is fine.
Definitely, sir, definitely. So, dear participants, I'm extremely happy to introduce before you today's another well-known guest speaker. Um, I'm very happy to introduce before you Dr. Ravi Kashikar. Dr. Ravi Kashikar is an associate assistant professor at the Department of Physics at Institute of Infrastructure, Technology, Research and Management, Ahmedabad, an autonomous university established by Government of Gujarat. Previously, he was a research assistant at the University of South Florida. He completed his MSc from Karnataka University, Dharwad, and his PhD from Indian Institute of Technology, Madras. He joined the Computational Nanoscience Group at the University of South Florida as a postdoctoral associate in the year 2021. Ravi's research experience mainly involves first principle based density functional calculations and tight binding model studies for halide and oxide perovskites. Ravi has published 22 research papers, which include JACS nanoletters and 10 physical reviews. Currently, he is exploring the finite temperature dynamics of halide perovskites. With these brief words, I now request Dr. Ravi Kashikar to go ahead with this presentation. Thank you, everyone.
Thank you, Dr. Samir Galgali, and inviting me to for this FDP program. So thank you to the principal sir, AICT, for this opportunity. And thank you participants. I know it is a hectic day, but you are here, and I hope I will not make you a boring session. At least will provide some of the interesting things on the quantum confinement and band gap engineering. So technically, I'm a theoretical guy, so working on the electronic structure of materials. So you might be knowing this part. So this is actually provides an insight about the material properties. So and I carry out the first principle based simulations, which is actually very insight. It provides a in-depth analysis what exactly happening in the microscopic level. Okay, so rather than doing an experiment, so when some of the times when you can't able to detect the physical phenomena that is occurring in the microscopic level, so you need to take an help of theoretical modeling, so which will provide an underlying interactions between the charge, spin ordering and all that. So the quantum confinement is also one of the process which has been explored recent in the later 90s to understand make the material 2D materials, 2D devices, right? So this is the where it started, although the idea borrows from the quantum mechanics, where we all studied the particle sitting in the box with having a potential well on the both the sides, which it can't jump out of that. So these are all been ideas of the quantum mechanical things, and we borrowed it borrowed it from the borrowed it sorry borrowed it from the borrowed it from the ideas of the quantum mechanics. Okay, so let me dive into this area. Okay, so we'll work on the some of the things. We'll show you some of the interesting facts, and I will show you how to model it from the first principle based techniques. One second, just give me 1 minute. Just 1 minute, sir.
Yes, sir. No problem, sir. Go ahead, sir.
Okay, sorry. Sorry for this one. Okay, so what is exactly it falls on? It falls on the condensed matter physics. So condensed matter physics, if you look at, so we actually probe the electronic, mostly the low energy, which we normally call it as a low energy or a milli-electron volt or electron volt physics. Okay, it has many things in that, which starts from the structure of the matter. It has the structural defects, defect interactions, crystals, phase transitions, everything. This is what we study actually in the whole condensed matter physics. Normally it has a different scales. Okay, so when I tell it is in a different scale, you can assume that it has a both, because we have been come up with the two types of, one is the space and the time. So in the space wise, it works in the case of micro or the nanoscale, or sometimes in the angstrom level as well. And in the form of time scale, you see it starts from the picoseconds to microseconds level, right? So this is the scales in which this whole condensed matter physics works, right? So what is exactly we do in all these processes? Okay, so we come up with the two things. This is very important in a condensed matter physics. This is one what we studied is the materials and the material properties, right? So how do we do that? We use two different techniques to understand the materials as well as the material properties. One is computational physics, and another is experimental physics. Both actually go hand in hand. Be careful that they are in a, although they are the different domains, but they go hand in hand. What is the aim of these two processes? These two actually helps you to understand the materials and properties, right? So one of the properties that is actually explored in the condensed matter physics is the quantum confinement, right? Why it becomes so important? Okay, so why this idea becomes so elegant in the condensed matter physics is because you can explore the materials in the length scale which is near to the de Broglie wavelength, right? So this is very interesting. We'll go into the details of that, but see how actually this is the de Broglie guy who actually changed the course of a quantum theory in a evolution of the quantum mechanics. Actually, the quantum theory would have been died. Quantum theory is almost completed in 1924, right? But the de Broglie asked the one question, the reverse question, that is, why can't a material behaves as a waves, right? And this is where to study all the quantum mechanics. You all know very well that it started from there, that point of levels. Okay, so we'll study what is actually the de Broglie wavelength and why it falls under this category. Okay, so this when we are looking at matter waves, which are of the order of the de Broglie wavelength, the things become very different from the classical physics, right? What is happening here? Although the energy which we know that it is a continuous, but it is changes. It's a continuity and becomes a discrete levels. Now the energies are not a continuous phenomena, not the continuous entity. It is a discrete in its nature. So this discreteness actually very interesting now. This discreteness creates a lot of interesting problems. Okay, so that's where we are entering into the totally different world, and that is a quantum world, right? So where we all these things can happen. These things can happen in a quantum wells, quantum wires, quantum dots. Okay, so this is the technical terms actually we are all know very well, right? So this is a whole together we call it as a nanostructures. But believe me, this some of the things can happen in a macroscopic level also, but they can't be. Those phenomena can be easily explained from the classical physics. But these, like a quantum confinement, okay. So this is where we need an help of quantum mechanics rigorously. Okay, so let's have an idea what is actually the de Broglie wavelength actually turns out to be, which you all know very well. So let's have a baseball of a 150 gram, okay, which moves with a 45 meter per second. So technically, if you look at this one, okay, the wavelength turns out to be 10 to minus 35. So don't you see this is the de Broglie wavelength? Obviously, this has a wavelength, but can we able to determine this wavelength is the question, right? So this is where right now, if you look at Look at all the instruments currently we have with us, right? So this is the typical wavelength, which is not at all possible from our current scenario to detect such a small wavelength, right? So such small wavelengths are, although every matter behaves according to de Broglie with the wave, but this is the very smallest wavelength which is not possible to detect. So we can utter, oh, okay, this is the classical particle, because the wavelength is not able to detect it, right? So let's go another way. Why? What is happening with electron? Okay, this is the case of a baseball, right? So now what will happen with an electron? Okay, so let's compare that electron with a photon. Photon, we know it is a kind of an electron, which is actually the dual nature of a light, where we have the wave, where the two hypotheses we know very well. But let's compare the wavelength of the electron, okay, because this is the entity which actually comes in the quantum confinement, right? What is the quantum confinement? We need to confine something, right? So and that is we are doing it in a materials, right? So when we are doing such things in a materials, obviously the electrons which is we are confining, right? So let's see, and we are confining. Why? Because there is interesting properties going to emerge from that. Okay, the very interesting properties which are not there in the bulk materials, those interesting properties are emerging. But to confine the electron, okay, to when the confinement can happen, okay, so that only the properties become very interesting only when it has a de Broglie kind of a wavelength. So let's calculate the electrons de Broglie wavelength for that. For example, if it is having a 1 electron volt energy, so let's compare that wavelength with the photon wavelength. Okay, so let's calculate the photon with the 1 electron volt energy. So that is, it's a very straightforward with the hc by lambda. So it is 1240 nanometer, or 12,400 angstrom. So that's the huge wavelength of that, a huge wavelength of a photon with 1 electron volt energy. So let's compare this the same with the electron, because electron has a mass. Now it is no longer you can call it as a classical particle, because it is having some kind of a finite wavelength which is actually detectable. Okay, so let's calculate from the same formula. So because it has a mass, right? So we will convert that into a kinetic energy. So we have 1.23 nanometers, right? That's the wavelength of an electron. Look at the dimension. Look at the value. This value. This value is turns out to be 12.3 angstrom, which is actually falls in under some of the electromagnetic wave range. So now this is very interesting. Earlier, when the discovery happened, so it is treated as a mass. It is treated as a particle because it is having a mass, which mass is we know it very well, right? So now, see, it is behaving as a wave now. See, you all know that both are in a different domains. Wave has a delocalization idea and the matter has a localization idea. But now it is a matter wave. When it is a matter wave, meaning that it should have a sum of the properties from the matter and it should have a sum of the properties from the wave. Right, so that is what we call it as a matter wave. So in the quantum confinement, this is actually is happening. This is actually is what we observe in the confined regions, right? That confinement regions, okay, you can relate that to the particle in a box. Okay, so particle in a box where we have a finite dimension. Okay, you can have a many things. See, the quantum mechanics actually works with the idea of two things, right? It is the idea of a wave function, okay, and the quantization of an energy levels. And all this can be possible only to that entity which is actually behaving as a matter wave. Matter wave means the particle which is now behaving as a wave, right? So it should have information of both localization and the delocalization. You may ask me a question, why I'm bringing all these things. Okay, so the answers for that is because you need to, matter is a localized entity, wave is a delocalized entity. You might be having, what is this electron is then? Electron will have a both information. That is why we will not define these things with the ideas of mathematics. We define with ideas of statistics. Why? Because in the statistics we have things called as a probability, right? Probably you can tell, hey, it is 50% delocalized. Means what? 50% it is localized. That's how we talk in a quantum mechanics. And in the confinement that happens between the two boundaries, okay. So in that case, the two things as is happening, it is quantized and there is a wave function exist. And now you may ask you a question, what is the probability of finding that matter wave in this region? Then you need to solve a Schrodinger equation. That's it. That's how we enter into the area of quantum mechanics. And you can see there's a huge difference. Although there is a big difference is there, but that doesn't matter because also this is smaller wavelength, but still it is behaving as an electromagnetic. Sorry, it is still behaving as a matter wave. Right. So where can we achieve all these things? Whatever I'm trying to tell, we put a two condition. We put a 2 to 3 conditions. We have to have the de Broglie wavelength and anything you can confine, that is okay, but electron is the easiest thing that we can confine. There is a possibility of confinement of some of the photons as well. Okay, that is a totally different physics because we are related to the material science. So we should be able to think about the electron precisely. And you may ask me a question, where can I all find these things, right? You can find these things in a many materials, but not in their pure form. Okay, you need to do something band gap engineering. I hope I'm making steps towards another side. Okay, so our first aim is to have a quantum confinement. Okay, but quantum confinement will not happen so easily. So we need to tailor something. We need to make the things alter the materials. How do we alter? We have many options. Okay, first is change the dimensions of the material. Go to the 1D, go to the 2D materials, go to the and so create some nanocrystals. That's what Dr. Poojar was talking about in the previous discussion. Okay, so we have a many ways to do this one. Okay, so one thing that I can clearly tell about is you cut it, work in a different dimensions of the materials. Right, that's how we created a graphene and other 2D materials and so on and so forth. And that's how the thin films become so powerful. So thin film technology becomes so powerful because of the things that can the quantum confinement things can happen. Right, so let's go. And what is actually is happening here? Although you see this is a bulk material. Okay, so in the bulk material always you will have a continuous energy bands. Okay, continuous energy bands. Okay, there is no gap between the energy level. This is a continuous process. Okay, so that's a very small energy difference between the levels. Right, so that's now, but the moment you start reducing the sizes, go into the different dimensions, okay, the slowly the energy levels will become quantized. Okay, and the separation becomes significant the moment you reduce the dimensionality. Right, so see here the two things are happening. Okay, by changing the sizes. Okay, so changing the sizes, the band gap, look at the band gap. Okay, so how clearly things are separating each other. Why it is what is the most probable answer for this one is because the electrons the motion of the electron is now restricted. Right, it is not allowed to move. It has a limited area and the limited area where it can move, and now it is slowly getting confined. Okay, so this is where the connections are happening now. This is where the connection is happening. The connection is that the confinements is indirectly altering the band gap. Fine. So what is the benefit out of this one? The benefit out of this one is that you can see many things can be achievable, because if some of the things are not there, okay, not there in the bulk materials. Now you can slowly starts appearing in the nanodot. That's a photoluminescence. Other photoluminescence is optical and optical properties, and something device engineering, and the mobility, everything of the electrons, property of an electron getting so and so changing from the one point to one dimension to the one size to another size. Okay, fine. So technically what I actually brought you to the level is that, okay, so technically I brought you to the energy levels. Energy levels of what? Energy levels of an electron. Okay, what is this? These are the states where the electrons actually these are just an energy levels, means you can call them as an these are having in terms of electron volt. But if the electron sits in this energy level, automatically it is going to have wave function. Correct? So ultimately you have an energy eigenvalue and you have an energy eigenfunction. Correct? So the two things, energy eigenvalue and energy eigenfunctions. To understand, because you see here, so see here, these are the energy levels, and the electrons, if it comes, so automatically it is going to have electronic eigenfunctions. So ultimately, how do you get all these informations? That's the question you need to ask, because I want to understand whether the quantum confinement is happening, whether the properties are emerging or not. So these are the technical questions you may ask you may ask, but how do we understand? Is it possible to understand from the experimental? Obviously, the highly sophisticated experiments will give you all this information. That's how we got a knowledge about that. But technically, it is not possible for every person who is working in this area, because such a highly sophisticated angle resolved photoemission spectroscopy, all those all those highly sophisticated instruments may not be available with everyone, right? So then we need to switch to the theoretical modeling, right? So today in this talk, I will gradually provide you an information about how these energy levels can be understood. Point number one. And point number two is that can we really do the band gap engineering and get the something quantum phenomena? I hope everybody is getting clear here in this point. So what is the importance? Can we able to understand these energy levels? Point number one. Okay. Can we now how this energy actually varies in the material? Okay. And the point number two is that what are the techniques that are available to me to understand such what are the techniques that are available, and how do we actually come up with the band gap engineering, right? So there are many ways. This is one. This is how actually the experimentally things work. So you will have many materials which have been actually called as an interfaces. Okay, so these interfaces, you see, we do develop one over other. Okay, the layer deposition. This layer deposition will create a different what should I say, a different energy band gap, because of the elements that are sitting here. Okay, so then what is going to happen? Then what is happening here is that this gallium arsenide will have a certain kind of a band gap, and this another aluminum gallium arsenide will have a certain other kind of a band gap. Okay, now I'm bringing close to them, right? So ultimately the electrons, they are sitting here. The electrons, they are sitting in this valence band, will slowly tunnel. Okay, because they have that energy to go, and they will come here, and that's how the electrons may come and sit and form and vice versa can also happen. Then the electrons sit here and forms a kind of a two-dimensional gas. So this is actually an idea. Actually, that's where it started, to create what? A two-dimensional gas. Okay, so this is how the really actually it looks like. Okay, so we have two different materials. We have two different materials with two different band gaps, and when I come too close to each other, right? So then they this is how the band engineering band bending will happen at the boundaries, and the electrons slowly drift from one level to another level and creates a new Fermi level, and that new Fermi level will now will be a kind of a new material itself, right? That is how it is happening. Okay, fine. So everything is all about the bands. Means bands mean the electron where it is sitting. Okay, these are the energy levels. These are the energy levels with which electron possesses. Okay, and where do these things exist? These things exist in a K space, means Brillouin zone. Okay, we everybody here we know Brillouin zone. This is where all these things exist. Okay, so how do we understand all this one? Okay, and ultimately we can solve a Schrodinger equation once they sit in those well, the electrons are sitting, and we can calculate the energy eigenfunction, energy eigenvalue and the wave function. This is what the three-dimensional wave functions I'm writing. This is what we write in the textbook. Okay, so technically more or less it looks the same, but more or less also it is same, but sometimes there will be a perturbations will be there. So we need to take care of the perturbations very well. And then if we solve the Schrodinger equations, it will be not exactly looks like the multiplication of the sign functions. It will have certain other quantity which has been multiplied here. So technically, more or less, we can calculate the wave functions and energy eigenvalue. This is very simplistic model which we studied in the textbook. But in a reality, it happens in a very different way, right? So it happens in a very different way. So let's study for that. Okay, so band gap engineering. So band gap engineering, where we can achieve a kind of a quantum confinements. Okay, so one thing is you can control the size. Okay, size means going into the different dimensions. Second thing is you can alloy. Okay, so you can alloy where the band gap also changes here. And the third thing is a strain, where you apply a stress and strain, stretch it. So for what I discussed previously, it is related to the quantum confinement. Okay, in the quantum confinement also, band gap changes. Now what I'm trying to tell from now onwards is that what are the ways to achieve the band gap engineering, because it has both, my talk has both the things. One is quantum confinement and band gap engineering. Okay, although there is much details are there related to the band gap engineering of the quantum confinement, but I'm more or less covering everything related to the band gap engineering, which is actually my core area, and I can give you a lot of details how one can take an information and work on that. Okay, so right, so let's see the two ways to make alloying. Third one is that strain engineering, apply a uniaxial stress, biaxial stress, apply in hydrostatic pressure, like that. That is the way how you can do, and apply the electric field or the doping effects. Okay, sometimes inserting the external quantities can also change the band gap vigorously, or you can apply an external electric field, because electron will react to the electric field. Okay, so then it can go. So 1 second, sorry. Okay, thank you. So what is happening is that, so you can do a kind of a different kind of a strain or stress engineering, then apply an electric field, and then go ahead and calculate the band gap of a material. What it will give, it can, this engineering will change the material properties. That is what we are interested. So by changing the material properties, okay, we use them for our devices. That is the ultimate purpose of a whole ultimate purpose of the material science and the material engineering, right? So let's start with that one. How do we start? So as I started with the two things, but now I will add the third part. Okay, so when I started my condensed matter physics ideas, I just talked about the materials and the properties. Although I did not specifically talk about the methods, but now I will be focusing on the methods, because we have a goal, we have a material, we know what we do, what we want to do. We want to come up with the materials where it can be used for the multiple purposes. That is the multifunctional properties. It can be used for It can be used for the quantum devices. It can be used for the sensor and other applications, and it can be used to generate a RAM, random access memories, and depending upon whether it is a magnetic materials or not, or it can be used for the optical sensors or optical properties, where it can convert the energies from one form to another form. Right, so everything can be understood from the materials and their perspectives. So how do we do that? How do we do that? There are the techniques that we, as I already told, it can be done with the two ways. Whether you do you can do with the experimentally, or you can do with the first computationally. Okay, then you tell the experimentalist, hey, look, this is how I have done the extracted the material properties. Can you now verify this one? Okay, so that is how you can propose the experimentalists, and then they will carry out and verify whether you are done it right or wrong, and then they will propose, yes, this is happening. Or the other way is that you can first experimentally do the things, and then an interesting phenomena can happen there. Okay, so then you do the computational study of those phenomena, and then provide the answers for that, why this is happening in this material. Right, so this is how these, as I told, these things go hand by hand. Okay, then only the interesting things can come up with that. Right, so let's see in the material science, what are the basic questions that we ask actually. How do we know that silicon is a good material for a silicon cell? How do we know that copper is a good conductor? How do we know that barium titanate is a ferroelectric material? So these are just questions from the material science perspective. Okay, so when I ask such kind of a questions, the ultimate answer is to do the experiments. That's how the historically these things has been done. Right, so but if you look at the if you want to come up with a very interesting material, and if you start doing an experiments on the experimentally known materials, but if our database says that you have a 1.3 million accurate 3D structure materials. Now if you start analyzing, okay, now if you start telling to the and start doing an experiments, okay, telling that, hey, this material is good for quantum confinement, this material is very good for quantum, this material is good for can be exhibiting the this property, and this material can be good for the band gap engineering. If you start doing an experiments on this kind of a database, it is impossible. Right, obviously it is impossible to work on such a huge set of materials. So what we do, and experiments, as I said, this has a time and costs and complexity that is there in the experimental designs. You know how the machines we work, machines are so costly. We, as developing countries, not every researchers has an access to work with the kind of an highly sophisticated material, highly sophisticated instruments, and ultimately the time and cost as also matters. Right, so what is the other way? Let's look at the other way, that is computational study. Right, so computationally you will have a lot of opportunities to work on that. Why I'm bringing this one? You may ask a question, why deviating from this point of view? This is possible. This is where you can come up with the various different designs. Okay, and tell the community, look, this can be possible. The most striking feature is the quantum confinement was studied computationally first. That is lanthanum aluminum oxide and strontium titanium oxide, LaOSTO interfaces. And that study, they confirmed first beginning, mentioning that the quantum confinement can happen in such kind of an interfaces. Right, so in this, and then later wise they did experiments on such kind of an interfaces, and confirm that ideas, that is existence of a two-dimensional gas in that quantum confined region between the LAO and STO was done computationally first. Then it was carried out experimentally and given a proof of that. Although the idea was there, but much earlier, but the computationally on the oxide perovskites was done using the computational, and that's why this kind of a study will be very useful. I will go on giving the lot of details to in the coming lectures, in the coming slides. Sorry. Okay, how actually it helps to study the band gap engineering and all that. Okay, so I will provide a small details how actually these things will work. Okay, so although you might be wondering our lecture, but I am not going anywhere from my title of the talk. Actually, I'm sitting there and talking to the way to understand the quantum confinement and the band gap engineering. I'm just developing the theories out of that. Sorry. So because of that, we were not able to, because here we will develop some of the things that are related to the computationally. Okay, so how this actually computational study actually revolves on that. This revolves on the three things. One is quantum mechanics, second one is the classical mechanics, and condensed matter theories. Right. So these three things is the mixture, or the mixture of these three things will actually provide a platform. These three things will provide a platform to study the material science. Okay, so how do we do all this one? So this is possible with the h psi is equal to e psi. This is what we solve in the computational physics. But is it this is very simple equation we are solving? No, the answer is no, because it is a very complicated very complicated second order differential equation. Okay, so this is actually is going to be solving. Okay, so we are going to solving the second order differential equations, but you may ask a question, what exactly it is going to provide? It is going to provide two things. One is wave function and the energy eigenvalues. This is what we need, right? This is what we need to understand the quantum confinements and the band gap engineering, because band gap engineering is where we are changing the energy levels. The moment we study, the moment we were able to get the information about the energy eigenvalues, which we obtained from the Schrodinger equation, then we can tell easily, hey, see, this is how the evolution of the conduction band is happening. This is how the evolution of the valence band is happening. Right, and the wave function, if we were able to track the wave function on the conduction band or the valence band, we can tell the properties of the material easily. Not the word easily is bit exaggerated. I would tell most probably we can able to tell the information of the materials by just solving this equation, right? So how do we solve these equations? Because as again, I will come to the electrons, because this is the electrons where the confinements, as I told, we are working on the material science. The electrons are the one which are actually confined. Okay, so now to understand the electrons behavior, what are its the regions where they actually sit. The electrons will sit in orbitals. Okay, so these orbitals, that is the SPD orbitals, which has a different quantum numbers, will actually form a basis to study the Schrodinger equation. Okay, this is where it will form the basis to the Schrodinger equation, and then it will provide information about the energy levels as well. How? Let's start. How do we will see how it starts actually. So this is the bonding. This is an electron orbit. Okay, this is another electron orbit, right? So now see, very interesting. As I told, when you are sitting in the bulk material, you have a continuous bands. But when I told you that I will change my dimensions, when I change my dimensions, slowly this continuity will be lost, and there will be a quantization of the energy levels will happen. That's what I told in the beginning of my introduction. Right, so now I will show you how exactly this is actually happens, means how this discretization is happening in the quantum confinement. So that is happening just looking at the formation of such kind of a molecular orbitals. This is the orbital. This is the orbital if there is only one electron is there. Okay, so now if there are two electrons are there, okay, so two different electrons from the two different materials are coming close to each other, and this is how it is forming a molecular orbital. Okay, so this molecular orbital, this is the molecular orbital. Okay, so this molecular orbital will actually where the electrons are sitting, coming from the two different things, right? So now you can see here, you can see this is the atom where the electrons are discretized. Okay, sorry, electron energy levels are discretized. Now this is the molecule where the two different atoms comes close to each other and they form a molecular orbital. How they are forming molecular orbital? Look at here. So you have a s orbital, you have a p orbital, right? So now if the two p orbitals of the different energy levels of the two different atoms come close each other, they form a molecular orbital, which we call it in the chemistry called as antibonding and bonding. Right, so this is an antibonding and this is a bonding orbitals. This is how this is how actually electron sits in the molecules. Now, if you only have a two atom system, which is now dimensionally you have reduced such a way that you only have two atom systems. Okay, so then this is how actually it looks. This is how the discretization happens. Now you slowly start bringing the different levels of an atoms. Okay, so now this starts the discretization will be lost. The discretization will be lost and the continuity will starts, because you are now bringing n number of atoms, meaning that you are increasing the size, means you are going towards from the quantum region to the classical region where you are increasing your size. This is what exactly happened in a reverse way. That is, if you now go from C to B to A, this is actually from the Ali textbook where we have studied all these things. Okay, this is how the quantum confinement is happening. We have a solid state, solid material. Slowly, if you reduce the dimensional, then this is how the discrete level happens. Then the electrons will sit here. This is electron will sit here, and then you go from the bulk to atomic level. That is how the confinements are happening. Right, and then the moment you have here, the velocity of the electron will be much larger, and now it can behave as a quantum particle. And now you all know how to calculate all this, right? But in a realistic materials, we have a scenario is a totally different, because normally we will have a large number of atoms, although we have a confinement by changing, although we have reduced the dimensionality, but still we will never come across a 2 atom 3 atom system. 100% we will have a lot n number of atoms, right? So then how do we study that one? Okay, so then this is the solid which is being formed now. Okay, now we can easily classify them as the crystalline materials and the amorphous materials. Okay, fine. So how do we study? This is the crystalline material, that is tin selenide. Okay, so I'm giving an example here, just a simple example I'm trying to give you. Okay, so this is the direct lattice and this is the reciprocal lattice, right? So this direct lattice and the reciprocal lattice, this is where all the atoms are. This is where the atoms are sitting. Okay. Now you know in the condensed matter physics we have a way to understand them both. We have a lattice parameters for this one, that is A, B, C, alpha, beta, gamma, and we have a space group, point group, everything that we can construct, and we can create a 7 crystal systems and everything. We can study this material. But you see, electrons as a quantum particle, it will not lie in a direct space, it will lie in a reciprocal space. Then we have to form something region, what we call it as a Brillouin zone. Right? So this Brillouin zone is where the electron is all the information of the electron exists. You see, if you do an XRD or any other kind of an experiment, all the information is actually hidden in this reciprocal space, right? So now this is what we need. How much time we have? 8:43. Okay, so I have come up for completed 45 minutes. Sir, Samir sir, just give me 1 minute, okay, sir?
Yes, sir. Yes, sir. No problem, sir. Go ahead.
Yeah, just 1 or 2 minutes. I will come.
Yes, sir. Yes, sir. No issue, sir. Go ahead.
Sorry, extremely sorry.
It's okay, sir.
Sorry.
Now you can share. Okay, sir. Go on, sir.
We have a international conference in next week, so that's why a bit busy. That's why. Sorry, sir.
I know, sir. I know. Yes, sir. Go on.
Yeah. So this is where we started. We have started the working on understanding the things in the direct lattice and the material in the Brillouin in the direct lattice, but all the information that exists in the Brillouin zone. Okay, so technically how it looks, if I tell you, I mean, beautifully how actually these things looks in the Brillouin zone, what I will do, we will do a toy model here. Okay, very simple toy model we will build here. Okay, what we will do is that we will construct a molecular orbital picture. Let's say a k.1. Okay, fine. So then I will do another molecular orbital that is at k2. Then I will construct another at K3, then another at K4. Like that, we will construct such a kind of a molecular orbitals in a different points in the Brillouin zone. Right? So this is what I will do. This is at any time, every time I am constructing. Right? Then I have accessed all the points in the Brillouin zone. Right? So at every point in the Brillouin zone I'm accessing, and then what I will do is that I will connect those energy eigenvalues. The moment I connect them as an energy eigenvalues, this is where actually electron is now sitting. It can slowly move from one point to another point easily, like that, right? And that is what we call it as an energy levels. This is how the actually energy levels are coming in a materials. This is how actually we calculate the energy values, right? So what we call this is as, we call this is as an electronic structure. Okay, so this electronic structure is plays a very, very important role in studying the materials in any dimension, anywhere the way that you want to study it. Means to tell the community to study the properties, to what are the different kind of properties that material exhibits and all that can be studied from the point of electronic structure. Right. So what is electronic structure? Electronic structure is nothing but a study of an electron. See, the simple definition. The simple definition is a study of electron behavior, how these electrons are distributed in a real space and in a different energy levels. That's it. That's how we study. And this is, you see, if you look at my beginning of the slides, in the beginning of the slides, this is what actually we need to study the quantum confinement. Is it right? So you can look at the electrons. You can, if you are able to study how these electrons are distributed in a real space and in different energy levels, and the moment you start changing the dimensions of the materials or do anything the way that you want, the moment you start evolution or you start studying how these energy levels are changing with the way that you are doing the externally, then everything can be studied from this one. By studying what? Studying electronic structure. Why this electron structure actually important? This electronic structure actually plays a very important role in determining the material properties. Not only many material properties: cohesive, equilibrium, crystal structure, phase transition, transport, magnetism, electricity, optical, and so on. Now, and not only that, we will not restrict to this. This is the bulk properties. We can go into the dimensionally. How actually dimension wise reducing, you can study the material in a thin film, you can study the material in a nanodot. Okay, if you start studying the things like that, then you can able to tell those properties where the confinement properties are emerging. The moment you study this electronic structure for a nanodot or a thin film, automatically the quantum confinement effects will come into the picture, and that will be seen in the data, means the output of this electronic structure. The changes that is happening in the electronic structure will tell you, hey, see this, the band is bending like this, the band is moving in a different direction. All these things can be easily understood from the studying the electronic structure. If you remember just previously we showed that band bending that is happening. The real band bending can be seen. The real band bending can be studied if you calculate the electronic structure of a gallium arsenide and the gallium aluminum arsenide together. You create a new crystal structure, right? You create a new crystal structure and calculate the electronic structure. The real confinement effects can be seen very beautifully there. That is why studying this electron structure, that is the title of our talk, that is quantum confinement, band gap engineering, how we study all these things from the theoretical insights, right? So now onwards I will give you a lot of examples how it can be studied. Okay, so this is the introduction. This is actually I should not say this is not how introduction should be, but this is what the extended introduction. Okay, so I laid down the two platforms. The first platform is the core idea, that is a quantum confinement. It is one of the property, actually. It is one of the process where the properties are significantly changing. That is the quantum confinement. And now in the second part, I give you the way to understand this one. way to understand this quantum confinement, and that is nothing but the electronic structure. And now in the third case, now I'm moving from the second to the third case, where I will give you the examples. We'll give you step-by-step examples where how this electronic structure study actually helped us to provide all the quantum mechanical related properties. I hope everybody got the clarity of my presentations. So it has a three structure of my presentation. One is we given a small introduction, that is the, and now,
sir.
Yeah.
Sir, are you changing the slides from the past? It is the same. This is the there, sir. Are you still on the same slide?
No, I'm changing tools to study the electronic structure. I'm studying.
No, sir. No, it is. Now it is coming, sir. Please, sir. Now it is coming.
Is it correct?
Yes, sir. Yes, sir. It is go on, sir. Go on. Now it is right.
Okay. So how do we study this? How do we study this electronic structure? Okay. So there are many ways to study that one. Okay. So that is a free electron model, nearly free electron model, tight binding approximation, or the density functional theory, or the GW methods. See, in the market, I mean market meaning in the subject. Okay, subject, we have so many things, processes or methodology has been developed to study this electronic structure. Why do we want to study electronic structure? Because we want to study the materials. We want to study the material properties. And then we have so many tools to do that. The first three, the free electron model, nearly free electron model, tight binding approximation, these are all we have studied in our textbook. The one that we have not studied is the density functional theory and the GW method. So the density functional theory is one of the powerful Nobel-winning tool that is given in the chemistry actually to study the material properties through what? Electronic structure. So the electronic structure is the main outcome from the density functional theory. Okay, so let's use this technique. I'm going to use this technique, and I will provide you some of the live examples. Okay, some of the examples that we worked on. And see, you may wondering that I'm slowly entering into the research topics, but my technical answer is no. I'm not entering any kind of a research kind of a topic, but I'm just providing how actually I will give in step by step and examples. I will not at all deviating from our core subject, that is a textbook quantities. Everything, whatever I'm going to tell now onwards, looks kind of a research kind of an topics, but it is technically a textbook kind of an information. Okay, so what we need, this is one of the interesting property. This is actually what we call it as a quantum materials. So these quantum materials, that is what we call it as a topological materials. Okay, what is this topological insulator material or topological? So there's a technical, the title of this example is topological insulating phase of halide perovskites under strain. Though it looks very big, but let me divide it into two parts. First part is that's the red colored one is a topological insulating phase. What do you mean by topological insulating phase? We all know insulating phase, right? We know everybody insulator. What is topological insulating phase? Nothing. So the surface, this is the material, this is the phase where we have a conductivity on the surface, but it is insulating in the bulk. That's it. Topology is a topic we know in mathematics, right? So topology is the one which actually having a same different kind of dimensions, sorry, different kind of a surface area which is being connected by something, a process. This is what we are using that technical term to our insulating phase. There is a material that is where the surface, if you calculate the conductivity of the surface, it is conducting. But if you calculate the conductivity of a bulk part, that is inside, it is insulating. That is what we call it as a topological insulating. Now can we able to get in some materials? What are those materials? Halide perovskites. Why we want to study halide perovskites? I will give you some reasons bit later. There is something reasons are there. And what is actually we are doing? doing strain. Why we are doing strain is a question that you can ask. The answer for this is very straightforward. We are doing actually band gap engineering. I hope I connected my title again one more time. The title, that is a band gap engineering. I specified many times how actually band gap engineering can be achieved. That is, the one process is a stress or a strain. I'm doing that one. What exactly I'm trying to, by doing a band gap engineering, I am achieving a quantum phase, a quantum insulating phase. Oh, sorry, quantum material phase or quantum phase in these materials. Right? So this is actually a story. Now you can ask me a question. How do we do that? What is the way to understand one? So there is two ways. That is a tight bending model and the density functional theory. I hope slides are changing. Right? Sir, slides are changing, right?
Yes, sir. Changing,
Yes, sir,
sir. Go
changing.
ahead.
Yeah,
ahead.
thank you. Okay, fine. So now what is this topological insulator phase? I already gave you the explanation, but I will give you one more time explanation in a different way. What is that? From the quantum mechanical perspective, because whatever we are doing is a quantum related part. Okay, so this is actually an outcome of a quantum confinement. This is actually an outcome of the quantum confinement that is actually studied in 1984 by von Kliching in Germany, where he was working on the Hall effect. He was actually trying to study the Hall effect, but not in a very known semiconducting materials, but to the two-dimensional material, two-dimensional gas. That two-dimensional gas of the electrons actually happened in an interface created by two different materials. That is due to the quantum confinement that has happened. Okay, so the electrons are freely moving in those two-dimensional quantum confinement space. Right? Then what he did is he applied an external electric field. Now the interesting thing started happening. That is, electron starts moving in a kind of orbits. That is what we call it as a cyclotron orbits. Okay. Now you see this is what is happening in the bulk part, means inside material. But the moment it is at the surface part, this is actually started making a incomplete motion, incomplete circular motion, and because of that there is a conductivity is happening in the surface or a edge. Okay, edge, what we call it as an edge. And now you see if you calculate the electronic structure, right? So there will be a kind of a conducting state between conduction band and the valence band. Right? And you see, this is all is an outcome of a quantum confinement. We're just applying in a magnetic field. This is what happened. Now let's go to the second version of that. What is that? Quantum spin Hall effect. This is again another phenomena emerging from the quantum confinement of the two-dimensional electrons that are sitting between the two different materials. Right? So now what we do, we will apply a two different way of a magnetic field. Okay, so one is spin up and spin down. Okay, so now the electron spins will play an important role. In this case, one of the electron spin will move in another direction, for example, up spin, and the down spin will move in another direction. This is what we call it as a topological insulator. See, the initial topological insulator actually emerged from the quantum confinement. Now this is what we call it as a quantum spin Hall effect. Right? Quantum spin Hall effect, because we have two states, conducting states in the edge. However, inside it is still a bulk, means it is still inside it is an insulating phase. However, at the edge it is a conducting. This one is the one actually idea derived and proposed theoretically and proven experimentally. Okay, some of the peoples. Okay, so Haldane, Thales, and Kosterlitz, these are the people who got the Nobel Prize in just 7 or 8 years back, that is in 2017, by just proposing this idea. right? So this is one of the phenomena, one of the live example of what the property that is emerging from the quantum confinement. Now, how do we achieve this one in a real material? This real material, it can be achieved by calculate by if you have a material, if you have a material where your spin orbit coupling is too high. What is spin orbit coupling? It is nothing but the coupling between the orbit and the spin. This coupling acts as a magnetic field. How interesting. How, and it will separate the spin up and spin down channels, right? So this technically creates a quantum spin Hall effect in the material, and now it can be termed as a topological insulator. But how do we understand all these things? Simplistic. Use the density functional theory. Use the density functional theory and calculate the electronic band structure. Okay, so the moment you can calculate the electronic band structure, how do you calculate? You calculate for the bulk and you calculate for the surface. There is a way to do that. Okay, the moment you do calculate the bulk, you can see there is a gap is there. So it is an insulator. But if you calculate at the surface, you see there is a conducting states are there. Kind of a Dirac cone, which is there in the graphene. Okay, so now same material, bulk, it is having a band gap, but on the surface it is having conducting states. This is what we call it as a topological insulator. What is the difference between the normal insulator? This is bulk, also band gap, surface, also band gap. So technically in a both the way it is having a band gap. This is a normal insulator, but this is totally different from the topological insulator. And that is topological insulator actually emerges from the electrons actually making a kind of a circular orbit in the two-dimensional gas, and they become incomplete in the edges. Okay, and because of that there is a continuity states are there, right? So this is how, this is one of the live example from the quantum confinement. But we studied in this, I will just skip this part because this is something else. Okay, this is not actually related. This is another way to calculate the confirm the topological insulator, but I will not discuss this one because not related to the band electron structure, so I will skip this one. Okay, so now I will move on to the how did we actually confirm such kind of a quantum phenomena in a materials. Okay, no, so there was in a 2013 one paper came. The paper actually said you very different. Okay, technically now I will give you some example to you. This is nothing but the electronic structure of a material. What is the material? Barium bismuth oxide. You know all the material. This is what we call it as an oxide perovskite material. Okay, so you see this oxide perovskite material. Okay, and what is this black regions? This is nothing but the energy levels of an electron. That's it. This is what we were actually our aim is to calculate. Now what is this M, gamma, X, MRZ? These are nothing but the different points in the Brillouin zone. If you remember my schematic in the Brillouin zone, I told you to calculate the molecular orbital picture at the different points of the Brillouin zone. Now you see this is what I have done. I have calculated the molecular orbital picture at the different points, and then I connected them by translational symmetry. Then I created this kind of an energy levels, right? So this kind of energy levels I created, and that is what I call it as an electronic structure. Okay, so you can see this is electron structure. Now you see there is a gap exist. You see, are you able to see this is a gap exist? But this gap is not in the Fermi level. This is a dotted line is a Fermi level. Okay, this is below the Fermi level. So technically it is a metal. But can we able to shift this Fermi level to here? Then it will become topological insulator. Correct. Okay, so this is how you can see the band gap. The gap is exist here. This is also gap exist here. Now what we will do? We will use our density functional theory and construct the molecular orbital picture. You remember how I was constructing the molecular orbital picture. Then you can see this how we can construct and then shift the Fermi level to the different energy levels. Okay, and then calculate the electronic band structure from the density functional theory. Then you can able to tell, okay, this material is a topological insulator. Means you can understand the material properties from this phenomena. Okay, I will not go into the detail of this one because this is a tight bending model. My aim is not to tell about the tight bending model. Okay, so this is all it is happening in this material. We come up with a schematic, very simple schematic, the textbook schematics, right? This is how the material looks. Okay, when the spin orbit coupling is 0, this is how the material looks when the spin orbit coupling is not 0. Then I will change the spin orbit coupling strength. This is how the band gap creates and changes. See, very simple switch on, switch off spin orbit coupling is creating a different kind of a topological states. What is this? This is again a topological material. Okay, understood from the electronic structure perspective. Okay, so this is the information, again in-depth information we can gather from the electronic structural perspective. You can tell, you can change the way that you want. How? What I did here is that instead of barium bismuth oxide, I changed it to from barium to sodium. So by doing so, you're changing what? You're changing the electronic states. Why? Because barium has a different electronic structure, sodium has a different electronic structure, but their valence state is same. In some of the cases it is a +1, and sorry, in a sodium bismuth oxide it is a +1 state and it is a +2 state. By changing this sodium to barium, I am changing actually the oxidation state of a bismuth and then changing everything. This is how another way of working on the band gap engineering. We change the oxidation states by changing with the different materials. Then everything is happening here, right? So you can see we did this one. We did change the various way interactions and all that, and now that is whatever we have calculated is on the bulk. But now we want to calculate the surface, right? Surface, it should show you conducting, right? Kind of a Dirac cone should come. Now you see beautiful Dirac cone is coming, confirming that this material is a topological insulator. How did we conclude this one? It is a quantum phenomena where electrons are moving with the relativistic speed because of the confinement, and the electrons electrons are behaving totally different in the surface and the bulk, right? So this is how the electronic structure helped us to calculate this one. Okay, so how much time we have, sir? How much time we have?
Sir, another say 15 minutes.
Okay, fine, sir.
10 to 15 minutes, sir.
Okay.
Thank you.
So my when I started beginning, I told you that that we will work on the halide perovskites. But so far I showed you oxide. What is the reason for that? As I told, technically oxides are very brittle. If you want to use it for any quantum devices, I want to tell you something more information about why this is playing a so important role. Because we are working and studying the quantum confinement. This is actually we are using in the quantum computers now. Okay, quantum computers are designed in a different levels. But one of the way to design the quantum processors is to build them on the topological insulators. The answer, what is the answer? Why you can ask, you may ask me a question, why is so? Because the thing that we got, that is a Dirac cone that we got in the electronic structure, is so powerful. It is impossible to destroy that Dirac cone by any external perturbations. So the external perturbations are not, it is protected by an external perturbations. So why it is so important? Because you can now access that electron which is moving kind of on a Dirac cone speed, and you can come up with a quantum state, okay, which is accessible for the quantum computing. And these states are protected by an external fields. Right? So now if you come up with a topological insulator, then it can be used for the quantum computing. Now you can see where I can, but now we have to go in a very small scale. But the oxide perovskites, so the oxide materials are very brittle. Now can we come up with a very soft materials, that is halide perovskites. These are very soft materials. Okay, the bulk modulus is very, very small, and it can be used for a flexible electronic devices. So you can see many applications. So my idea was to come up with the topological insulators in these halide perovskites. You can see, and it can come up with a very, very different categories. It is completely inorganic, completely hybrid organic, inorganic. It is many, many ways it will come up. Now there are very, very various varieties, various way where you can design this hybrid organic, inorganic perovskites. Okay, so this is, and there is a many way that these materials are also ferroelectric materials. Some of these materials are ferroelectricity. Now you can change the state by applying an external electric field. You can change the states of these materials. So that is the advantages of this halide perovskites, which is the problem in the oxide. So my interest was to work on this kind of stuff. Right? So now you can see there is a differences between, again, there are many differences between these materials. Okay, you can see structurally they are very soft. The piezo, they have a, if you apply an external pressure or stress and strain, okay, so you can change the polarization of the materials. By doing so, you can come up with the piezoelectricity. Optical electronic devices, they are useful for the optoelectronic devices, and so on and so forth. These are very, very interesting properties of the halide perovskites. Now what I did is that I applied an external pressure, okay, to these materials. This is the electronic structure of the material. It is a normal insulator. Okay, now I applied a pressure of 4.3 gigapascal, and you can see I created a kind of a Dirac cone in a bulk. And slowly I increased the pressure. Okay, I created a state which is having a bulk, it is a band gap. But if you see the surface, it is now having a Dirac cone. Interesting. This is what we call it as a topological insulator. Well, where we achieved this one? We achieved this one in a hybrid organic inorganic perovskite. Okay, so idea is that, so now this material is a technically a quantum materials. It was a very classical normal insulator, but by just working on the band gap and the band gap modulations, we now converted that material into a topological insulating material. Fine. Okay, so now we applied a various kind of a stress and strain, and this is how the band gap is changing. You see, slowly a band gap actually, you can see this color. Okay, you can see it is a color. It is going from the positive to negative. What do you mean by negative band gap? Negative band gap is nothing but where we exchange the energy eigenvalues of the conduction band and the valence band, and this is what we call it as a quantum state, where the band gap is actually band gap, where the characters of the valence band and the conduction bands are actually changing here. Okay, and that is what it is happening in the topological insulating phase. Okay, so what we did this one by changing the external strain, biaxial strain, the way that we achieved this one. And we worked on the different kind of systems where we applied again hydrostatic pressure and studied the band gap. Again, you can see this is how the band gap is changing, slowly decreasing, and there is a point and it breaks down and enters into the topological insulating phase. This topological insulating phase, which is actually which is actually a quantum phenomenon, quantum confinement phenomena, we were able to now achieve in the bulk material itself. And it creates a very beautiful surface states, which is looks like a kind of a Dirac cone, which is a quantum relativistic quantum mechanics. And this is what it is happening here. And then now we understood why it is happening, how it is happening, everything we studied by using the density functional theory and the electronic structure. Okay, and this is how the live example of one of the quantum confinement phenomena. And second one is we studied the band gap engineering by changing the composition of the materials. Okay, by doing that, we were able to find then applications to the LED as well. Okay, so this was funded from the government of India. Later, again, we gave an example how this is happening in this material. Okay, and the third example that I want to give you is that by applying an external pressure. Okay, by applying external pressure, we were able to go into the another new electronic device, that is a spintronic device, spin field effect transistor, which is actually where we spin role, means quantum role, that becomes a very important factor. And we were able to study how this actually spins arrange themselves in a materials. Okay, so this is we studied by applying an external pressure. Obviously, there is a band gap change was happening, but we studied how actually spin changes goes from the directional change. Earlier it was X direction. Now you can see now it is in a Y direction. What is the way to change? By applying an uniaxial stress, compressing and expanding. By doing this one, we were able to tune the spin texture in the materials. This is the now, rather than working on the electron, we are working on the spin now. And this is achievable by the external pressure. How the band gap and everything is changing, you can see this is the conduction band, the difference between the energy levels. This is, you see, beautiful how the bands are rearranging themselves with respect to the pressure. And you can see the band alignment changes the way with the pressure. And we were able to calculate the polarization, energy, and all that. Right? So the beautiful picture about again the how spins change with the pressure and the band gap changes with the pressure. So with this, actually, I have many things to tell, but we'll stop it here because there's a lot of details will go into this phenomena. This is, you may ask you, this is all quantum phenomena. Whatever I am showing is related to the quantum phenomena where the electrons behave kind of a matter waves and come up with a very different, the properties will emerge from this one. Okay, so ultimately the take home message from my side is that to achieve such kind of an confinements or any quantum phenomena, we need to play with three things. One is a crystal, orbital, and spin. If you are able to successfully play with this thing one, okay, you can achieve various different quantum phenomena, that is antiferromagnetic ordering, which is another way to understand from the quantum mechanics. The main striking feature is quantum materials, where you have a topological Dirac wheel kind of materials. And if you additionally able to tune the ferroelectricity, then it is very helpful because you can able to change the directions as well. Okay, so with this I will conclude my discussions. I'm open for questions. Okay, you can ask me any questions or can send me messages here. I will try to explain again more. Okay, so I will stop here. Thank you, everyone.
Ravi sir, thank you so much.
Yeah.
And let us wait a minute or two so that if any participant have any questions, he may ask, but it was such a beautiful discussion, sir. And
Thank you, sir.
I could able to remember my teacher's words when he says, as mathematics develops, technology develops. And I
Yeah.
hope your presentation strikingly tells the same fact that theoretical physics too is an important component in the area of design and devices, especially.
Yeah, obviously,
And
sir. We are now close to with the AI and ML. We are now close to the experiments. Hopefully, there will be a day where we will reduce the burdens of an experiments, where they will not they should not struggle for the funding or the all the problems they face due to the machines and all that. We our theoretical models will, I mean, scale in a very such a high level sometimes in the future.
true, sir, true, very true.
Yeah.
Participants, if you have any questions to ask, you can.
Thank you, everyone. You stayed up to this time. Thank you. Okay, if anybody, any one or two questions, I'm ready to answer.
Yes. You can also post it in the chat box. Dear participants, is it okay if I post feedback link in the WhatsApp group?
Sir, it's okay. You can share anywhere, no issues.
No issues. Then thank you. Thank you so much.
Thank you, sir.
Yes, sir. Thank you so much, sir.
Thank you very much. Thank you.
Sir.
Thank you.
Yes, sir. Yes, sir. You can. No, sir.
Yeah.
We will call you later, sir. Huh?
Yeah, sure.
Yes, sir. Yes, sir. Yes, sir. Thank you so much. Thank you. So, dear participants, thank you so much for this being present for this enlightening session. Can I now request the last? Please open your just open a video for a minute or two, please. Everybody. It takes me just 1 minute. I will take picture and then you can. Your video, please. Thank you. Thank you, everyone. Thank you so much. Thank you. Thank you. Now, let us join tomorrow again at 6 p.m. only. We will start sharp at 6 p.m. So I hope everybody will be there. Thank you extremely. We will see you tomorrow then. Thank you. Thank you very much.
Thank you, sir. Thank you. Thank you.